There are countless, unusual celestial bodies scattered around the vast expanses of the universe. A combination of various factors has turned some of them into mysterious anomalies, exceptional even by space standards. Some of these objects are amazing exoplanets, strikingly similar to Earth, while others have never seen sunlight or experienced heat. There are worlds torn by continuous sandstorms, while others are covered by a vast ocean whose bottom is made of blocks of glowing ice. At the same time, in the depths of multicoloured nebulae, there are giant stars capable of swallowing whole planetary systems, and millions of light years away from them, jellyfish galaxies cut through the expanses of space with their shining stellar tentacles. And today, we invite you to join us on a fantastic journey to the most incredible ones. Kosmo. The first in outer space. Before we set out on a space journey beyond the boundaries of our system, we have to decide on the manner of selecting a planet that resembles the Earth most from thousands of candidates. What should be the parameters of this fascinating world, and what should we take into consideration first? It goes without saying that planets favorable for the genesis and sustenance of life have always posed considerable interest to scientists. However, it is no easy matter to single out suitable celestial bodies among a great number of those discovered by now. To have clear-cut selection criteria, scientists worked out the so-called Earth Similarity Index, or ESI for short. It is based on several principal parameters: a planet's radius, density, and average surface temperature. This combination makes it possible to calculate the object's mass, approximately estimate its chemical composition, gravitational level, whether or not there is an atmosphere, and if there is, analyze some of its characteristics. It also helps establish if there is liquid water on the planet's surface and other information. The standard of this index is the Earth, with its parameters assumed as ideal and its ESI equaling 1. Based on the Earth Similarity Index, all the objects known to us conventionally fall into three categories. The first one is objects whose ESI is under 0.5. These are for the most part gas and ice giants, as well as extremely hot or on the contrary cold objects. This is the category most of the solar system planets and satellites fall into. It takes just one characteristic to greatly exceed the maximum permissible values for a celestial object to be unfavorable for the genesis and sustenance of life. Let's take Venus, for instance. The radius and mass of this celestial body are very close to those of the Earth. However, due to its close proximity to the Sun and a dense atmosphere, its surface temperature is extremely high. That is why, in spite of a close similarity to the Earth on the face of it, Venus's ESI is not high, at just 0.44. Of course, there being any life on its surface is totally out of the question. Celestial objects whose ESI is within 0.5 to 0.7 fall into the second category. These objects resemble our home planet noticeably more. They are mostly rocky worlds with relatively moderate temperatures, but it can also be ocean planets and even some large satellites. Incidentally, a high Earth Similarity Index per se does not warrant favorable conditions for life. For example, quite often low-mass planets are incapable of retaining a dense enough atmosphere, while their magnetic field is too weak to protect the surface from lethally dangerous radiation. Other celestial bodies yet may happen to be located too close to their parent star and so get tidally locked. Of course, all these factors greatly reduce the chances of life's genesis and sustenance. As for the third category, it contains celestial bodies with a high ESI, that is over 0.7. All of these planets are beyond the solar system. According to estimates, the size of these worlds and the conditions on their surfaces are potentially close to those of the Earth. Among these planets, there is one which resembles ours most, and it lies just 12.5 light-years away from the Earth. This amazing world orbits Teegarden's star, a small red dwarf discovered in 2003. This star is 1,370 times dimmer than the Sun. This means that it cannot be observed with the naked eye, even though it lies quite close to the Earth. The mass of this tiny star is roughly 9% that of the Sun, and its radius is about 5% bigger than that of Jupiter. Gravitational forces are barely strong enough to maintain the thermonuclear reaction in the star's interior. That is why the surface temperature is just 2,900 Kelvin, or roughly 2,630 degrees Celsius. As is the case for all red dwarfs, Teegarden's star's habitable zone is comparatively narrow and located very close to it. Back in 2019, 2 exoplanets were detected in its system after continuous observations of the star's proper motion. Interestingly, one of them lies beyond the star's habitable zone and the other within. The outer planet, dubbed Teegarden C, follows an almost ideal circular orbit around the system's center. With the orbit's radius 0.045 astronomical units, it is completed every 11.5 days. It is presumably a rocky celestial body with a mass 11% bigger than that of the Earth. Its radius is estimated to be approximately 3.5% bigger than that of our planet. Unfortunately, conditions on Teegarden C's surface are far from hospitable. Due to the low luminosity of its parent star, the object enjoys 63% less energy than what the Earth receives from the Sun. As a result, the planet's surface temperature is gauged at 47 degrees Celsius below zero on average, which is too low for life sustenance, at least in the forms we know it. Still, the chance of there being vast oceans of salty water concealed under a thick layer of ice on Teegarden C, as is the case with Jupiter's satellites for instance, shouldn't be ruled out. As for the inner planet, it is dubbed Teegarden B. It is actually this planet that is the most Earth-like object of all those discovered to date. Its CSI is 0.95, which is just 0.05 less than the standard ideal value of our Earth. This celestial body lies 0.025 astronomical units away from its star, and it takes it roughly 5 days to complete a full orbit around it. By following a practically circular orbit, the exoplanet is constantly in its star's habitable zone, and it receives 15% more radiation from it than the Earth from the Sun. According to some estimates, Teegarden B's mass is just 5% more than that of our planet. As for its radius, it differs from that of the Earth by a minuscule ratio, which means that the gravitation value is also quite close to what we're used to on our home planet. This makes it logical to assume that the inner makeup of the exoplanet is highly likely to be similar to that of the Earth. There is a massive metallic core coated in a thick layer of molten silicate mantle reckoned to be at the center of the planet. The celestial object's outer part is covered with a relatively thin crust of solidified rocks. Mathematical modeling shows that the average temperature of Teegarden B is 28 degrees Celsius, which is 14 degrees more than that of the Earth. This means that conditions on its surface allow the planet to have and retain an ocean of liquid water, and the planet's temperature profile is potentially favorable for most microorganisms. Even though Teegarden B is quite massive and is capable of retaining a comparatively dense atmosphere, the radial velocities method, which is used for exoplanets detection, is quite inadequate for obtaining any information about the atmosphere's composition. But it should be borne in mind that a planet's temperature profile directly depends on its atmosphere's composition. For example, a dense atmosphere with a high percentage of methane and carbon dioxide will cause a strong greenhouse effect. Dense clouds of water vapor, meanwhile, will on the contrary reflect sun rays, which reduces temperatures. We should also remember that no matter how optimistic the parameters of this fascinating celestial body might appear, it is not entirely flawless. Being in close proximity to its parent star, it seems that Teegarden B is always facing it with one and the same side, which causes sharp temperature differences between the day side and the shadow side. As I've already mentioned, Teegarden's star is a red dwarf, and this class demonstrates a tendency to suddenly flare up. The amplitude of fluctuations in its luminosity may reach 30%, which greatly affects the planets located close by. Still, the chances of Teegarden B's capability of sustaining life are high. Biological creatures often demonstrate incredible viability, and their ability to adapt can't but amaze. For example, the ocean could serve as protection against lethal radiation and sharp temperature fluctuations. Its upper layer is potentially capable of absorbing cosmic radiation, while its currents could dissipate temperature contrasts. For all we know, as time goes by, primitive organisms might evolve in the warm depths saturated with energy and microelements. Just a tiny chance is sometimes enough for life to develop into something bigger. As a rule, it's potentially habitable planets with favorable conditions and a moderate climate that especially catch one's attention among the great diversity of other worlds out there, or else, on the contrary, extremely dangerous objects stand out among others. Still, there is yet a third category. It's anomalous celestial objects manifesting unusual behavior which is barely scientifically accountable. Objects like that challenge our knowledge and deserve special attention. This is exactly the kind of world we'll be looking at now. The year 2009. The environs of the Kepler 413 system. An unknown object passes between our planet and a distant star, briefly reducing its luminosity. Astronomers take this event to be a standard exoplanet transit and announce the discovery of a new celestial body. High-precision calculations even make it possible to determine its parameters. The planet turns out to be a cool giant, with a mass of about 25 times that of the Earth and a radius of about 40% that of Jupiter. However, 180 days later, another expected transit never occurred. The planet, so clearly visible in the old data, seemed to have vanished without a trace. A dark spot in the photosphere of the star, or a giant dust cloud moving in its vicinity, would have accounted for the mysterious phenomenon. But these hypotheses were dispelled when 800 days later the mysterious object reappeared just as suddenly as it had vanished. The hypothetical planet eclipsed the disk of its parent star 5 times before disappearing again. Still, the key to the riddle had been found. It turned out that Kepler 413b has a highly unusual orbit. The celestial body is located near a binary star and is 0.36 astronomical units from the system's common mass center. Its trajectory is constantly affected by gravitational perturbations, and the change in gravitation of 2 nearby stars shifts the orbital plane considerably, causing cyclic oscillations. When the deviation reaches its maximum, the object leaves the line of vision and then returns to it. Calculations show that Kepler 413b's orbit oscillates with a periodicity of about 11 years, deviating 2.5 degrees in each direction from its average value. The planet's own axis of rotation also changes its position significantly, with a maximum angle of inclination of up to 30 degrees. Combined with a notable eccentricity of the orbit and its periodic shift, the climatic conditions on the surface change in a bizarre way. The region that receives the most light from the parent star is constantly shifting from the equator to the poles and back, which leads to dramatic variations in temperature. It is likely that this process generates huge planetary-scale hurricanes, which can be larger than the Great Red Spot of Jupiter. Air currents can carry ice clouds at several kilometers per second, gradually becoming unstable and dispersing. Meanwhile, the collision and deformation of vortices is capable of causing tremendous atmospheric emissions that have the power to overcome the planet's gravity and reach outer space. According to calculations, they will hang a while up there before gravitational forces pull them back down. All these incredible phenomena make the planet a rather harsh place. However, it may seem like a tranquil, serene island in comparison to the following world. "190 light-years from Earth. The environs of the HD 10606 system. This yellow dwarf, surprisingly similar in parameters to the Sun, is orbited by a planet with a highly variable climate. It whizzes towards its parent star as rapidly as a giant comet, burning itself in the hot rays of its corona, only to retreat to the periphery of the system. The object is a gas giant, with a mass 4 times that of Jupiter, and a radius slightly different from that of Jupiter. At the furthest point in its orbit, the planet is 0.88 astronomical units away from the parent star, and receives about as much heat from it as the Earth does from the Sun. It has been suggested that this is when clouds consisting of water vapor droplets, ice crystals, or even microparticles of quartz may condense in its atmosphere, and temperatures on the surface of the hypothetical satellites of the gas giant could be comparable to those on Earth. But as the planet gets closer to the star, conditions on it change very quickly. Within 55 days, the distance between them shrinks by a factor of nearly 30, and the energy flux from the star increases by a factor of 800. Observations show that at the lowest point in its orbit, the exoplanet's temperature roughly doubles within a matter of just 6 hours, from 500 to 1200 degrees Celsius. Such drastic changes result in violent hurricanes, which can reach speeds of up to 5 kilometers per second. By absorbing an incredible amount of heat, the atmosphere of the gas giant expands so fast that it produces shock waves capable of sweeping across the entire planet multiple times. Water vapor is broken down into oxygen and hydrogen by the temperature, and quartz crystals evaporate without a trace, only to recondense into gigantic sand clouds later. In all likelihood, HD 80606b is the only planet in its system. The gravity of another nearby star has not only warped its orbit, but has also wreaked havoc on the protoplanetary disk. So the chances of encountering other large objects nearby are rather slim. However, destabilization of a planetary system due to the interaction of celestial bodies is not uncommon. "1,530 light-years from Earth. The environs of the Kepler-36 system. The central object in this system is a yellow subgiant. Its mass is comparable to that of the Sun, and its radius is 62% larger than that of our star. There are 2 planets rapidly orbiting the star, a rocky super-Earth and a hot mini-Neptune. Every 97 days, they mutually approach at a critical distance of only 1.9 million kilometers, about 20 times less than the minimum distance between the Earth and Venus. At such moments, their mutual attraction causes global cataclysms, but after a few days, the celestial bodies diverge again until the next resonance. According to calculations, the gravitational interaction between the planets at the point of closest approach is about 13 times higher than that between the Earth and the Moon. In particular, this effect should be seen on the surface of the rocky planet. Under the influence of titanic forces, its crust may crack and shift, causing earthquakes of incredible power. The resulting chasms may be hundreds of kilometers long and cause multiple eruptions of gigantic volcanoes. It is likely that some regions of the planet do not cool down in the short period of relative tranquility, creating seas of eternally bubbling, red-hot magma. The reasons for the formation of such an unusual system are still debatable. We now know that the super-Earth, dubbed Kepler-36b, is 0.12 astronomical units away from its parent star, and it takes 14 days to complete a full orbit around it. The super-Earth's mass is 3.8 times that of the Earth, and its radius is 1.5 times that of our planet. The object has been calculated to have a temperature of 980 Kelvin, or just over 700 degrees Celsius, and an average density of about 30% higher than that of the Earth. The data suggests that the celestial body could be a Chthonian planet, the core of a gas giant that has lost its atmosphere. Such objects contain many heavy metals like iron and lead, as well as sulfur and silicon compounds. It is likely that the light elements that once made up the thick, dense shell of the celestial body may have been blown into space by stellar wind. Nor should we forget the second planet's gravitational pull, which could potentially have contributed to this process. The object is called Kepler-36c and is likely to fall into the class of hot mini-Neptunes. The celestial body moves in a nearly circular orbit with a radius of 0.13 astronomical units and completes it every 16 days. Its mass is 7 times that of our planet, and its radius is 3.7 times that of the Earth. Because of its proximity to the star, the temperature of the object is also very high, 928 Kelvin, or 655 degrees Celsius. This celestial body should be surrounded by a thick, multi-layered atmosphere consisting mainly of nitrogen, hydrogen and helium. Deeper down, the pressure inside the gas shell increases and it gradually turns into an ocean of supercritical fluid surrounding the solid core. Meanwhile, under certain conditions, truly fantastic phenomena are also possible. For example, the gravity of a more massive planet can potentially capture satellites from its smaller companion, while tidal forces may destroy them to form vast asteroid streams. In addition, the mutual gravitational pull of the two planets distorts their orbits, altering eccentricity and other parameters. Because of this, the entire system behaves chaotically and unpredictably, and its evolution cannot be predicted over any extended period. Modeling shows a 91% probability that the two planets will collide with each other over the next 70 million years, producing hundreds of thousands of pieces of debris which will disperse throughout the planetary system, thereby creating a still greater chaos within it. Such tremendous cataclysms may have occurred more than once in the following system. 434 light-years from Earth. A surprising object, informally called Super Saturn, is located 4 astronomical units away from a young Sun-like star. It is a brown dwarf, or a large gas giant, 20 times as heavy as Jupiter. Observations show it to be a young planet, about 15 to 16 million years old, which is still forming. Most of its atmosphere consists of hydrogen and helium, with a massive metallic core in its depths. This object is spun by a system of rings, like Saturn's but much larger. The transit method revealed at least 37 distinct rings, with the largest one's outer radius measuring about 0.6 astronomical units. This is comparable to the size of Venus's orbit, and about 640 times the radius of Saturn's rings. According to calculations, the total mass of the circumplanetary disk is bigger than the mass of the Earth, and its behavior manifests signs of randomness. Mathematical modeling shows that such structures are not stable and gradually disintegrate. Some of the objects making them up lose velocity and fall to the central planet, while others, on the contrary, accelerate and leave the disk forever. However, this process is greatly extended in time and may take several 100 million years. Also, a large rupture with a radius of about 0.4 astronomical units was detected in the system of rings, which is considered indirect evidence of the existence of an exosatellite in this region, about 80% the mass of the Earth. According to current understanding of the physics of space objects, it is a kind of object capable of clearing its orbit of small debris, forming a wide rupture in the ring structure. In addition, Observations suggest the presence of at least 2 more celestial bodies, with a mass of each of about 30% that of the Earth, and located at a distance of about 0.25 astronomical units from the center of the brown dwarf. Just like it is the case with the large planets known to us, it can be assumed that a total of several hundred exosatellites, including rather massive ones, may be located within the gravitational influence of the central object. A simulation of such a system, including radiation from a parent star, heat flow from a giant planet, and tidal influences, shows that the temperature of the celestial bodies making it up could approach comfortable values. One can only imagine how enchanting the night sky would be from the surface of such an exosatellite. At this distance, the brown dwarf occupies 70 times as much space in the sky as the full moon, and its soft glow can dispel the darkness and turn the night into a misty twilight. Instead of the star-spangled canopy, the planet's sky is crisscrossed by vast swathes of light from horizon to horizon. At the same time, the tidal forces of a nearby massive body could provoke multiple eruptions on the satellite's surface, and its hypothetical ocean could slam the land with giant waves. The width of a tidal zone under such conditions could reach hundreds of kilometers, making it a unique climatic zone, something like a cross between land and the ocean floor. Still, it should be mentioned that such structures tend to be unstable and change their appearance quite quickly beyond recognition. It is difficult to say how much longer we'll be able to admire the giant rings and what they will look like in millions of years. Assumptions about the existence of space objects the size of a planet, which are independent from any star, have been around for a long time. Such celestial objects, freely drifting around interstellar space, are referred to as orphan, free-floating or rogue planets. Astronomical bodies of this kind emit very little thermal and light energy into space around them. It is suggested that there are no bodies in their close proximity they could clearly interact with or be bound to. That is why it is hardly surprising that these objects are so difficult to detect. The first potential representatives of this class of planets were spotted as recently as in the early 21st century. The warmest rogue planets can be detected with infrared telescopes, and others thanks to something called the gravitational microlensing effect. As one would expect, this class of celestial objects is one of the most mysterious and understudied. Today, only 3 astronomical bodies can be classified as rogue planets with a sufficient degree of certainty, with the overall number of rogue planet candidates over 24. Incidentally, according to the analysis of data collected in the course of the Ogle project, the Milky Way may supposedly be home to up to 100 billion objects of this class. This may only mean that right now we're at the very beginning of an upcoming series of discoveries in this field. Our notions of what rogue planets are like have long been based purely on assumptions and hypotheses. With the technological advancement of highly sensitive observation equipment, there arose opportunities to put them to the test in practice. The rogue planet lying closest to the Earth among those already confirmed is known as WISE 0855-0714. 7.27 light-years away from the Sun, it was detected in 2014 with the WISE Orbital Infrared Telescope. The astronomical body cannot be seen through optical telescopes, as it emits no visible light to speak of. The reason for this is its extremely low temperature, from 225 to 260 Kelvin, or 48 to 13 degrees Celsius below zero. In terms of its parameters, it resembles a cooled-off gas giant, and its age cannot be under 1 billion years. The rogue planet is mostly made up of hydrogen. However, in 2016, the Gemini Observatory produced evidence of the presence of large amounts of water in its atmosphere. It is suggested that water is condensed into clouds made up of tiniest particles of ice. Today, it hasn't been established for certain how this object came to be, There are currently two versions suggested by researchers. According to the first one, a celestial object like that starts its life cycle in the protoplanetary disk of a regular planetary system. Mathematical modeling of this process shows that if the original cloud of gas and dust is heavy enough, it is highly likely that at least one planet will be ejected beyond the system. The celestial object may also be forced out of its star's environs if another massive star passes it by, or else if its planetary system collides with another system. The chances of events like that are admittedly comparatively small. The other version has it that the space object was born just like any other star on compression of interstellar gas. At the same time, the mass of the object proved to be too small to unleash any thermonuclear reactions in its interior. It goes without saying that in this manner it may turn out only as a gas giant or a brown dwarf, but not a rocky planet similar to the Earth. Some researchers don't agree that these objects should be seen as rogue planets and classify them as sub-brown dwarfs instead. Others suggest using the term planemo for all interstellar wanderers that don't show any thermonuclear activity. Bearing in mind today's notions of the makeup of brown dwarfs and gas giants, we may estimate the mass of WISE 0855-0714 at anything from 3 to 10 Jupiter masses. This rather falls short of starting a thermonuclear reaction, but quite enough to keep the heat effectively trapped inside the planet. Taking into account our knowledge about natural laws, we can predict what the conditions on the astronomical body's surface are like. For example, according to research by David John Stephenson from the University of California in the US, gas giants similar to Jupiter don't cool off instantly after receding from their star. Their thick hydrogen atmosphere is quite reliable thermal isolation, while the dense and hot nucleus made up of metallic hydrogen can keep the planet heated for a considerable time. Estimates show that the temperature of the lowest strata of a hypothetical celestial object's atmosphere may be high enough for liquid water to be around. It is likely to be present in the atmosphere as giant clouds made up of tiniest droplets. These deductions agree with the results of mathematical modeling of WISE 0855-0714 carried out by a team of scientists from the University of Edinburgh. It showed that the most likely temperature value of the planet's surface is 250 Kelvin or 23 degrees Celsius below zero. The celestial body's atmosphere also has a comparatively warm layer around 100 kilometers thick, whose density fluctuates from 0.4 to 1.2 milligrams per cubic centimeter. It is comparable with the conditions on the Earth, and so it is thought that this environment should be favorable for potential organic life. Incidentally, a planet doesn't have to be a massive gas giant to avoid freezing in the cosmos. In 2020, a rogue planet candidate was detected using gravitational microlensing techniques. And here is the long designation it got. It is still awaiting confirmation of the rogue planet's status, and its parameters have been defined only generally so far. According to preliminary data, however, the object is comparable to the Earth in terms of its mass, and is anything from 30 to 180,000 light-years away. According to our current scientific notions, an object with a mass like that is not supposed to be a gas giant, and is more likely to be a rocky planet. This, in its turn, offers good grounds to believe that the object formed in the protoplanetary disk of a planetary system as the latter was forming. It may have been ejected from the system as a result of a cataclysm in space, or alternatively under the influence of a larger neighbor. After that, it was left to its own devices and so became a free-floating planet. What will happen to it next is predefined by a combination of several factors. Provided the object's atmosphere is sufficiently dense, it will be reliably thermally isolated. Potentially, a layer of ice on its surface could produce the same isolating effect. In addition, with the object's interior scorching hot and with radioactive elements undergoing decay, most of the hypothetical ocean will remain in a liquid state. If the planet happened to have a moon, it may have retained it on ejection. If this is the case, tidal forces are likely to continue to deform and warm up the lithosphere, Theoretically, with any luck, primitive anaerobic life forms may have stayed around, although of course it would be next to impossible to discover their traces now. Most of the data about the rogue planets we know today were arrived at following mathematical modeling and complex calculations. It was possible to do these calculations thanks to the tiniest bits of information gleaned with the help of orbital and Earth-based telescopes. Even as I speak, a project is being worked on known as Cleopatra. Its main objective will be to search for free-floating planets and other objects in space with subsequent definition of their parameters. The project relies on something called microlensing. It is a phenomenon when a celestial body passes between a remote star and the observer on the Earth and briefly interferes with the light emitted by the remote star in the background. When observed from different angles, the moment of transition will be registered a fraction of a second sooner in one observatory than in another. Referred to as lensing parallax, this effect allows scientists to gauge the distance to a detected object, as well as its mass and dimensions. An interplanetary spacecraft is planned to be created within the project. It is supposed to blast off the surface of the Earth as soon as in 2025 alongside a mission to Mars, after which it will enter its own orbit around the Sun. The project will be aided by a specialized artificial intelligence component, whose mission will be to process and analyze collected information. The Cleopatra project will certainly delight us with a wealth of exciting and important information, so there is a lot to look forward to. What is to become of all those rogue worlds out there, drifting quite by themselves in the dark depths of the universe? In theory, an orphan planet may be captured by the gravitational field of a star and become part of its planetary system, but this chance is by all accounts minuscule. Most objects like that are destined to wander for billions of years through endless expanses of space, while slowly and inevitably cooling off. Eventually, they're to be swallowed up by black holes, or else destroyed as a result of a cataclysm in space, never to reveal their secrets to mankind. The year 2003. As the starry sky was being routinely observed, a small yellow dwarf was detected in the Phoenix constellation. It was later to be dubbed WASP 96. The year 2013. The Super WASP Orbital Telescope detected an extremely rarefied gas giant in the immediate vicinity of the star. A preliminary spectral analysis of its atmosphere revealed that it was remarkably transparent and practically devoid of any water vapor. The year 2022. Analysis of the object's atmosphere was conducted again, this time with the help of the new generation orbital telescope James Webb, which offered an unprecedented accuracy. Scientists were taken aback. If the new data were to be believed, the exoplanet was supposed to be shrouded in thick layers of clouds, which was the exact opposite of what the previous observations had revealed. Thus, the data from the James Webb was in conflict with the earlier estimates, and the degree of our understanding of the universe was questioned yet again. So, what is this amazing telescope like? And what has it seen in the depths of space so far? Let's take a closer look at it. The history of the largest modern orbital telescope began back in 1996. Its development and modernization took as long as 25 years, after which the spacecraft left our planet and set out on its journey through space. It took James Webb a month to reach its destination point, located 1.5 million kilometers from our planet. Because the telescope is equipped with high-precision infrared sensors, it can see the dimmest and most distant space objects hidden in the depths of the universe. However, this unmatched sensitivity also has a downside. The intense radiation from the Earth, the Moon and the Sun interferes with the faint signals of distant stars and exoplanets. Therefore, in order to counteract this effect, the super-sensitive instruments were covered with a multi-layer heat-reflecting screen. The observatory itself had to be moved away from large celestial bodies and be located near the so-called second Lagrange point in the shadow of our planet. Still, the obtained results were absolutely worth all the effort, because James Webb helped us make quite a number of amazing discoveries pretty much from the very first days of its operation. With some of them quite expected, others, on the other hand, prompted additional questions. One of the studies with a paradoxical outcome was the spectral analysis of WASP-96b, a glowing exoplanet of extremely low density. It is located 0.045 astronomical units from its parent star and completes a full orbit around it in just 3.5 days. According to calculations, the mass of the celestial body is half the mass of Jupiter, and its diameter is 20% more than that of Jupiter. Because of the extreme proximity to the star, the temperature of the object's outer layers is quite high and reaches 1285 Kelvin, or just over 1000 degrees Celsius. Exoplanets of this type fall in the category of hot Jupiters and are distinguished by large losses of atmosphere due to stellar wind. Earlier measurements showed very clear lines of sodium in the atmosphere of WASP-96b, which was interpreted by the researchers as a sign of an unusually clean and cloudless atmosphere. The fact is that according to the available models of the structure of gas giants, this element can exist only in the planet's interior. As we can see traces of it, it means that the upper regions of the celestial body's atmosphere practically do not absorb light. It was assumed that thanks to this, the ultra-sensitive detectors of James Webb could look into the deepest layers of the exoplanet. However, the information obtained by the telescope turned out to be radically different. The outer layers of the gas giant contain great amounts of water vapor. It condenses in the upper atmosphere and can form a large haze or thick clouds, reflecting some of the light shed on it. Because of this, the temperature of the lower layers of the object may differ significantly from the calculated values. Perhaps the accuracy of the earlier study was insufficient, or else some of the data was misinterpreted. It is also possible that we do not yet know of a certain factor that would allow us to combine the results to form a single correct picture. WASP-96b remains a mystery, which means it still needs to be studied in more detail. Of course, James Webb's discoveries do not end there. For example, 69 light-years away, there is an unusual system consisting of 3 brown dwarfs at once. These cosmic bodies are too big to be planets and at the same time too small to launch a stable thermonuclear reaction in their interior. Brown dwarfs are usually difficult to detect, as the radiation of their surface is extremely low. But James Webb sees the universe primarily in infrared, which makes it easy to distinguish objects that are virtually invisible in the optical range. The 2 largest components of the system are very similar in their characteristics and are located quite close to each other. The distance between them is about 2 astronomical units, and their total mass is slightly more than 100 times that of Jupiter. The temperature of both objects is relatively high, reaching 2600 Kelvin or slightly over 2300 degrees Celsius. The third component of the system is at a much greater distance, about 100 astronomical units from the center. Its mass is between 14 and 23 Jupiter masses, and its radius is 20% more than that of Jupiter. Also, this brown dwarf is about twice as cold as its more massive companions. Observations reveal that the temperature of its outer layers is 1240 Kelvin or slightly below 1000 degrees Celsius. Nevertheless, the celestial body is considerably warmer than the gas giants in our system, especially given the absence of a star that would give it heat. It was surprising to find that the outer layers of this brown dwarf contain not only the usual components such as water, methane or carbon dioxide, but also minute particles of various silicon compounds. The simplest of these is quartz, but more complex substances have also been detected. These are thought to be concentrated in the atmosphere of the celestial body in the form of vast clouds. The existence of such clusters had previously been predicted from theoretical considerations, because silicon, being a product of stellar thermonuclear reactions, is quite widespread in the universe. Still, until recently, observations have not been able to confirm this hypothesis. It is thought that about 140 million years ago, there was a single gas dust cloud in the system's place, which later split into 3 independent clumps. This event may have been caused by the gravitational influence of a massive celestial body that passed close to the protostellar nebula. Remarkably, if the separation had not occurred, the total mass of the formed object would have been enough to start a self-sustaining thermonuclear reaction. In this case, instead of 3 brown dwarfs, we might have been observing a single tiny star. Incidentally, the James Webb equipment is capable of observing not only single objects tucked away in the depths of space, but tremendous space structures as well, that stretch for hundreds of light years. One of them is the Orion Nebula, which is one of the largest stellar nurseries in our galaxy. This bright and vast cluster is located about 8,500 light-years from the Earth and has a mass of up to 900,000 suns. It contains not only giant clouds of interstellar gas and dust, but also thousands of stars, from the smallest ones to the most gigantic. This is where 2 of the Milky Way's brightest objects are located: Eta Carinae and WR25. The luminosity of each is several million times greater than that of the Sun. Unique objects like that certainly attract astronomers' attention. Besides, James Webb's infrared cameras are able to pick out great numbers of stars in the dusty haze, which were previously unknown to us. The point is that it is in this area in space that hundreds of young stars are constantly getting born. According to modern concepts, new stars are formed by gravitational forces that compress and heat up clouds of cosmic dust. During its evolutionary process, a protostar goes through several stages until finally a thermonuclear reaction kicks in its interior. This theory has been confirmed by multiple observations, but many details of this long and complex process currently remain understudied. The formation of a new star sometimes takes millions of years, but astronomers don't need that long to observe it. Thanks to James Webb's infrared sensors, thousands of protostars and young stars at various stages of evolution have been detected in the Orion Nebula. It is important to note that all these objects formed within the same gas cloud, which means that they are very similar in terms of composition and age. By observing them, researchers can fully trace the process of star formation and better understand what forces are involved. Some phases of this process, predicted only in theory, take hours or days, and with James Webb, the chance of capturing them is greatly enhanced. For all we know, we may soon be able to admire a photo of a young star flaring up thousands of light years from the Sun. Meanwhile, an 18-section mirror 6.5 meters in diameter and an onboard array of high-accuracy instruments allow James Webb to capture light from objects much further away, at the very edge of the visible universe. They are more than 13 billion years old, giving us a glimpse of the earliest times immediately after the hypothetical Big Bang. However, even James Webb would not have been able to see their luminescence but for one unique coincidence. The phenomenon of gravitational lensing has long been known to scientists. This physical phenomenon helps us to better see into the depths of the universe. And this is how it works. A powerful gravity generated by a massive body focuses and amplifies the light from a source behind it. Such an effect can be produced only on condition that a great many factors happily combine, so it is not surprising that it is one of the rarest phenomena in the universe. It is all the more surprising that while observing the galaxy cluster SMACS 0723, located about 4 billion light-years from the Earth, James Webb captured light of a space object passing through gravitational lenses as many as 3 times. In total, the radiation was amplified about 20 times, without which astronomers would hardly have been able to distinguish it from background noise. The object is thought to be a distant and very old galaxy, whose age is estimated to be 13 billion years. About 10 other star clusters have also been detected, which are thought to have originated between 200 and 700 million years after the genesis of the universe. According to some observations, they have a complex structure which takes tens of millions of years to form. This discovery will allow scientists to develop the existing ideas about the early stages of the universe's evolution and may even prompt to question its age. Unfortunately, we still know very little about such remote times, and James Webb will surely help us learn more about them. Exoplanets differ very much in terms of their environment. Their dimensions may be enormous, some even beating Jupiter, but there are also comparatively smaller ones, close to our Earth in size. Some of these bodies are hot, consumed with oceans of molten lava, whereas others are encased in a shell of permanent ice. There are planets out there made entirely of oceans, with not a bit of dry land on them, while on others sulfuric acid rains or diamond snow are a regular occurrence. Various techniques are used for discovering other worlds. As a rule, it is next to impossible to spot an exoplanet by simply looking through a telescope. That is why in 2009 Kepler was launched, the first space telescope designed for searching for planets beyond the boundaries of the solar system. The telescope's cameras had 42 charge-coupled devices, or CCDs, with a total resolution of around 96 megapixels. With a field of view covering about 25% of the sky and coupled with a 1.5-meter mirror of the telescope, it was able to detect astronomical bodies within 3,000 light-years from the Earth. In the 3.5 years of productive operations, Kepler managed to spot over 3,500 exoplanet candidates. The status of over 2,000 of these has already been confirmed by repeated observations. It was in this period that the smallest of known exoplanets today was detected. The diameter of Kepler-37b is just 35.7% that of the Earth. The telescope was also instrumental in registering several stars and brown dwarfs. The transit method was used by Kepler in the search for exoplanets. This method is based on observing the star's luminosity. If the supposed planet passes between the parent star and the observer, this will be noticed in the telltale decrease in the star's luminosity. The extent of these fluctuations in luminosity directly depends on the ratio of the star's and planet's dimensions, while their regularity allows one to estimate the object's orbital period. The transit method requires accuracy in measurements. Changes in a star's spectrum account for less than 2% and are usually tenths or even hundredths of 1%. Ripples in the atmosphere, dust and precipitations negatively affect results produced by Earth-based telescopes. That is the reason why telescopes based on automatic space stations are used for searching for objects beyond the boundaries of the solar system. Unfortunately, in 2013, 3.5 years into the mission, the Kepler Space Telescope had several major equipment failures. In 2018, the spacecraft ended science operations completely. Kepler was the first spacecraft to be created specifically for looking for exoplanets. However, most of the objects it managed to spot happened to be too remote and dim to study them in any satisfying detail. That is why the next space research complex had slightly different parameters. Kepler was succeeded by the TESS telescope launched by NASA on the 18th of April 2018. Its main object was searching for rocky exoplanets orbiting the brightest stars within 200 light-years from the Sun. This telescope also used the transit method. And here is the spacecraft's brief profile. TESS is equipped with 4 refractors with a 24 by 24 degree field of view and a 10 cm aperture. The spacecraft's peculiar orbit allows it to cover both the northern and the southern parts of the sky, which is approximately 85% of the entire sky. Photos are taken by 4 cameras, and the resolution of each camera's CCD is 16.8 megapixels. TOI 700d is one of the most notable objects discovered by TESS. This exoplanet became the first object of the kind comparable to the Earth in size, and which found itself in the habitable zone of its star. It orbits TOI 700, a red dwarf lying slightly over 100 light-years away from the Sun. It is a small and rather cold star. Its temperature is half that of the Sun, and its mass and radius are just 40% those of the Sun. TOI 700 is peculiar for its high stability. Not a single flare has been registered on it since the beginning of observations. A star's stability is a positive feature, because bursts of activity are able to divest its planets of their atmospheres and be generally pernicious for potential life on planets' surfaces. There are at least 3 planets orbiting TOI 700. The one closest to it, TOI 700b, is comparable to the Earth in size. Its mass is approximately 1.07 times that of our planet, and its radius differs from that of the Earth by not more than 2%. Unfortunately, TOI 700b is too close to its host star. It is within about 0.06 astronomical units, and a year on the planet lasts just 10 days. In addition to that, chances are it is tidally locked, that is, it faces the star with one in the same side. This means that the planet is likely to be scorching hot. The planet lying further from its star, TOI 700c, is thought to be a mini-Neptune. Its mass may be from 5 to 13 times that of our Earth, and its radius is 2 or 3 times that of the Earth. It takes TOI 700c 16 days to complete one orbit around its host star. Located closer to the star than the inner border of the habitable zone, it must be too hot for life to originate and evolve there. TOI 700d is the third and at this point the remotest planet in the system discovered by now. It takes 37.4 days to complete a full orbit, which by the way lies along the inner edge of the habitable zone. The mass of TOI 700d hasn't been gauged precisely, and may be anything from 1 to 3 times that of the Earth. At the same time, the planet's radius is just 20 to 30% bigger than that of the Earth. TOI 700d is thought to be a rocky world, but its exact composition is not yet known. The amount of energy received by the planet from its star is 86% that of the amount we receive from the Sun. Assuming the planet's atmosphere is similar to ours, the steady-state temperature on the surface of TOI 700d is estimated at 268.8 Kelvin, or 4.3 degrees Celsius below zero. However, due to the greenhouse effect, or other features of the atmosphere we may not know yet, this figure may shift either up or down. There is no precise data on the eccentricity of TOI 700d, but it is thought to be small at around 0.11. As the planet's orbit finds itself at the inner edge of the Goldilocks zone, the planet's eccentricity, however small, may incidentally turn out to be perceptible when the planet comes too close to its star from time to time, thus actually leaving the habitable zone. Still, with a year on the planet lasting slightly over 1 Earth month, such unfavorable periods are expected to be rather short. If there are living creatures on TOI 700d, then they might be able to weather the harsh spells in a state of anabiosis. Alternatively, they could adapt or migrate to less inclement areas. Even though the data acquired by spectral analysis of TOI 700d can't be enough for making conclusions, there is a chance that there is liquid water on the planet's surface. Then there is bound to be the greenhouse effect too, which will help the surface temperature to reach favorable values. As I've already mentioned, TOI 700d, along with the other known planets in the system, is highly likely to be tidally locked to its star. If this is the case, there should be a stark difference in temperatures between the sunny side and the shadow side. This contrast could be leveled off by a dense atmosphere, but that would cause powerful hurricane winds. Although the main mission of TESS has been accomplished by now, it still has enough resources to carry on operations. The telescope will continue taking snapshots of the sky, including the Milky Way plane, which is the most challenging direction for observation. Over 2,100 exoplanet candidates have been discovered by TESS in the course of the main mission. Not less than 66 of them have already been confirmed. Apart from that, 6 supernovae flares have been registered, 3 exocomets identified, and a great number of photos taken of small bodies in the solar system. The latter were not objects of the main mission, but are of course of scientific interest. Shortly before Halloween in 2020, NASA compiled a list of the most terrifying worlds. Among others, they included 6 exoplanets. Each of these objects' environments is not just extremely harsh for any living organism, even finding oneself in their comparatively close proximity may prove to be fatal. The first object on the list is a black gas giant, designation TRES-2b. This celestial object orbits the star TRES-2, which is a yellow dwarf lying as far as 718 light-years away from us. Let's take a closer look at it. Due to some unique properties of the chemical composition of the surface of TRES-2b, the planet absorbs over 99% of all the light shed on it. The nature of these properties remains a mystery, and chances are there are some chemical reactions taking place on the surface that we have never registered on any similar object before. And it is these properties that make TRES-2b the darkest exoplanet on the astronomical map of today. This gas giant was discovered on the 21st of August 2006, with more details on its characteristics obtained several years later. The mass of TRES-2b is 1.2 Jupiter masses, and its radius measures 1.27 times that of Jupiter. The atmosphere is as scorching as 1000 degrees Celsius, which gives the exoplanet a faint red glow like that of embers. Still, in spite of its gloomy looks, TRES-2b doesn't really qualify to be called the most dangerous place in the universe. There are many more objects lurking in space that are more terrifying than that. Let's see some more inhospitable ones. Here is another exoplanet, designation 55 Cancri E. It lies in the system of a Sun-like star, designation 55 Cancri A. This celestial object was discovered on the 30th of August 2004 by the Doppler spectroscopy method. Let's look at it in more detail. The planet's mass equals approximately 8 Earth masses, and its radius measures 1.875 that of the Earth. 55 Cancri E is tidally locked, and so it is always daytime on one side and nighttime on the other. That is why the side facing the host star is always heated up to a temperature reaching 2400 degrees Celsius, with the temperature on the night side 1300 degrees Celsius. These values are so high because the distance between the planet and its parent star is just 0.0183 astronomical units. Besides, volcanism on 55 Cancri E, which is thought likely to be there, causes dust clouds emissions. These clouds trap heat and effectively prevent it from escaping into space. The planet's orbital period is slightly under 18 hours. As for the atmospherical makeup, There is helium and hydrogen registered in it. There are also large amounts of carbon. Incidentally, this element is likely to form thick layers of graphite and diamonds in the planet's interior. 55 Cancri e isn't the only object in the planetary system of its host star. There are 4 other celestial objects orbiting it. The environments on these are by far more hospitable, which is the feature by which the 55 Cancri A system differs from the following object. It is dubbed Poltergeist, or PSR 1257+12c. This is an exoplanet lying in a pulsar system. The celestial object is located just 0.36 astronomical units from the system's center. This shows that Poltergeist wouldn't have survived a supernova that must have taken place before the pulsar had been formed. Consequently, the exoplanet is likely to have formed after this tremendous event, with the material for it coming from the nebula left after the explosion. According to another hypothesis, the pulsar may have formed after the merging of 2 white dwarfs. Unlike with a supernova, this process isn't always accompanied by a powerful blast. Still, as this is the first object of its kind we have discovered, science cannot give a definite answer as to its origins. The system with the celestial object lies 2,300 light-years from the Earth. Its mass is approximately 4 times that of our planet. As for its orbital period, it is around 66 days. Incidentally, the outstandingly powerful radiation emitted by the pulsar is enough to crumple any spaceship wanting to approach the mysterious exoplanet in its system. Even with all these properties taken into account, Poltergeist does not really qualify as the most dangerous exoplanet known to us. On approaching it, an astronomical body may simply get destroyed, but it would get positively vaporized in close proximity to the following object. The reason for this effect is the extremely high temperature on Kepler 70b, which is the hottest exoplanet known to us. The object orbits the subdwarf star Kepler 70. With a surface temperature higher than that on our Sun, it reaches 6,800 degrees Celsius. The object's mass equals 0.44 Earth masses, and its radius measures 0.76 that of the Earth. The celestial object's orbital period is 345 minutes. In other words, a day here is less than 6 hours long. Interestingly, the exoplanet regularly passes another object in the system, Kepler 70c, at a distance of 240,000 kilometers. To date, this is the closest that planets in space have been registered to pass each other. The extremely high temperature on Kepler 70b could be accounted for by the fact that this object may once have been part of its parent star. As for giving it the status of an exoplanet, it will take more evidence to confirm that it deserves to be given it, so this remains an open question. It should be mentioned that Kepler 70b is not the only celestial object we know of that interacts with its parent star so closely. Another object in similar conditions is the exoplanet known as WASP-12b. This celestial body lies 870 light-years away from our system. Its radius measures 1.93 times that of Jupiter, and its mass equals 1.46 Jupiter masses. WASP-12b is just 0.03 astronomical units away from its parent star. Due to this close proximity, the exoplanet has a temperature reaching as much as 2,200 degrees Celsius. The host star's extremely powerful gravitation slowly absorbs WASP-12b. Eventually, in approximately 10 million years' time, the exoplanet is expected to be destroyed completely. Bearing all this in mind, we will probably never delve any deeper into the nature of this exoplanet. It would appear that studying worlds of this kind cannot be high on scientists' list of priorities. However, some of these objects may happen to have some really unique features. Seemingly quite plain and ordinary, worlds like that may conceal many more dangers than would appear at first glance. When flying past the celestial body HD 189733b, for example, one might complacently think it a safe planet, as it resembles our Earth by its looks. But if one were to get as low as the level of its atmosphere, one would be exposed to some life-threatening dangers. For a start, the object's winds carry particles of silicate and develop velocities of 8,700 km per hour. Besides, the rains on this planet cause precipitations of molten glass. The reasons for such hazardous weather conditions are extremely high temperatures and the atmosphere's peculiar chemical composition. Speaking about the exoplanet's orbital period, it is approximately 2.5 days. And it is highly likely that the object is tidally locked to its parent star. As usual, a quick overview of its main characteristics. HD 189733b is a bright blue gas giant orbiting an orange dwarf in the constellation Vulpecula. It lies just 63 light-years away from our system. The object's diameter is 1.1 times that of Jupiter, and as for its mass, it is 113% that of Jupiter. Interestingly, the distance between HD 189733b and its star is 30 times less than the distance between the Earth and the Sun and equals approximately 5 million kilometers. Due to its close proximity to the parent star, it has a constant surface temperature of as high as around 930 degrees Celsius on the day side, with the temperature on the night side never dropping below 425 degrees Celsius. Immediately on being discovered, the celestial body became a subject of investigations. In 2007, thanks to data obtained by the Hubble telescope, scientists found out that HD 189733b has a foggy atmosphere. Interestingly, when the planet transits between the observer on the Earth and its star, its atmosphere assumes a reddish hue. This effect could possibly be caused by the haze in the atmosphere. According to preliminary estimates, it consists of particles of iron, silicates, and aluminium oxide. Apart from that, the information beamed back by the Hubble telescope helped scientists establish that the planet's atmosphere contains water vapor, neutral oxygen, and an organic methane compound. Additional investigations revealed the presence of carbon monoxide on the day side of the planet. What prompted most questions, however, was the results of investigations revealing traces of methane of an unusual variety in the planet's atmosphere. This chemical element was shown to be in a peculiar fluorescent state when it emits electromagnetic radiation in the infrared range. This state of the substance is indicative of some unknown activity in the atmosphere of the exoplanet, which still remains to be found out. This is quite a clear-cut example of a situation when investigating an object like an exoplanet with an exceptionally harsh environment may yield unexpected results about some processes taking place there that will be a valuable contribution to science. And as the process of studying these worlds continues, they will remain no other than horror planets to us, as well as a solid reminder that we're more than just lucky to be the dwellers of our Earth. The first steps in theoretical confirmation of there being ocean worlds out there, that is, planets fully covered in water, were made back in the 1970s. That is when evidence was found that radioactive decay in a planet's interior and tidal forces may cause water ice to melt and subsequently form huge oceans. In all likelihood, similar processes take place on Jupiter's and Saturn's satellites. However, these celestial bodies remain icebound as they lie too far away from the Sun, whose rays would otherwise melt the thick layers of ice. But when we talk about an ocean planet, a slightly different type of space object is meant. The term implies that the ocean on a planet's surface isn't concealed under a layer of ice, and its depth measures more than 100 kilometers. Theoretical calculations of these planets' formation and evolution processes were carried out in 2004 by French astrophysicists headed by Christophe Satin. According to this theory, if the mass of a forming planet is more than 10 times that of the Earth, this starts to actively attract hydrogen and helium from the gas and dust cloud around it, In this manner, with time, it grows into a gas giant. By contrast, if this planet's mass is just 6 to 8 Earth masses, the new planet is going to be comprised of ice and rocks roughly in equal measure. Just to compare, the mass total of all water in the global ocean on our Earth accounts for just 0.025% of the Earth's total mass. In this case, provided a space object's orbit lies far from the host star, this object is going to be either an ice giant or a cold super-Earth. Radioactive decay taking place inside the core will help melt some portion of the ice, which in its turn will help form a subsurface ocean, but the planet's outer layers will still remain frozen. If the planet happens to find itself in its star's habitable zone, its outer layers will melt and spill all over the surface in a boundless ocean. Theoretical calculations show that a planet with a mass 6 to 8 times that of the Earth may have a layer of water over 100 kilometers thick. The pressure exerted by this amount of water may reach 20,000 atmospheres, depending on temperature, impurities and other parameters. This is enough for some special exotic varieties of ice to form, like ones remaining solid even at high temperatures. In addition, unlike the familiar water ice, these modifications would be heavier than liquid water. For example, the density of ice 7, which is likely to form in these conditions, should be around 1,650 kilos per cubic meter. This ice settles on the planet's ocean's bottom and forms a massive cryosphere that envelops the more massive core. The opportunity to put these theoretical assumptions to test arose when a tiny and dim star was spotted 42 light-years away from the Earth. It was dubbed Gliese 1214. The diameter of this red dwarf turned out to be 5 times smaller than that of the Sun, with its mass just 15.7% that of the Sun. At the same time, Gliese 1214 is 300 times dimmer than our parent star, while its surface temperature is only 3000 Kelvin, or 2700 degrees Celsius. There is nothing particularly remarkable about the star itself. To be blunt, it is just another nondescript red dwarf that looks like any of the billions of other stars in our galaxy. However, in 2009, a solitary planet was detected in its environs, which was dubbed Gliese 1214b. With its diameter measuring 2.5 times that of the Earth, this exoplanet is just 6.5 times heavier than our home planet. Straightforward calculations show the freefall acceleration on the exoplanet's surface to be just 91% that of the Earth. The average density of Gliese 1214b is approximately 1,870 kilos per cubic meter. Judging by this comparatively small value, the exoplanet cannot realistically be made up of mostly metals and rocks, as is the case with our Earth, for example. But incidentally, this average density value seems to confirm the assumption that the astronomical body is 75% water or water ice and just 25% rocks. Thus it appears safe to suggest that this exoplanet is an ocean planet. The object lies very close to its host star. The average distance between them measures just around 2 million kilometers, or 0.014 astronomical units, which is 75 times smaller than that between the Earth and the Sun. Also, the orbit eccentricity is rather high at 0.27, slightly more than that of Pluto. This means that in its perihelion, Gliese 1214b is approximately twice as close to its star than when in its aphelion. As for its orbital period, it takes the planet about 36 hours to complete it. The red dwarf Gliese 1214 may be 300 times dimmer than the Sun, but this incredible proximity to the star makes the climate on Gliese 1214b scorching hot. Supposing the reflection coefficient of the surface of Gliese 1214b is the same as that of Venus, the planet's surface temperature is supposed to be around 393 Kelvin or 120 degrees Celsius. If, on the other hand, the surface is darker, the temperature may reach as much as 553 Kelvin or 280 degrees Celsius. Due to the fact that the orbit of Gliese 1214b crosses the star's disk, scientists are able to carry out spectroscopic investigations of its atmosphere. Still, the results are rather ambiguous. If this space object really is an ocean planet, its atmosphere is supposed to predominantly consist of water vapor with some accompanying gases. Interestingly, no lines of hydrogen, helium, or complex substances like water, CO2, and ammonia have so far been detected in the planet's spectrum. It is thought that the outer layer of the dense atmosphere conceals its true content from the observer. The conditions on the surface of Gliese 1214b remind one of what it is like inside a giant steam boiler. Interestingly, the atmospheric pressure in its lower strata should be at least 15 times as high as that of the Earth. As the ocean and the atmosphere are in a state of thermodynamic equilibrium, the border between them is rather blurred. No wonder, as the density of water vapor just above the ocean's surface is practically equal to that of constantly boiling water. As we look deeper at the lower strata of the ocean, the pressure will continue to increase until we reach the depth of 100 kilometers. With the pressure value at this depth, water will be unable to remain in its liquid state even at temperatures this high, and so we will see the bottom made up of dense and heavy ice, whose thickness is estimated to be upwards of 5,000 kilometers. Thus, most water on the planet is concentrated here. Below the cryosphere, there should be the core, made up of rocks and metals. Unfortunately, chances of life evolving on any ocean planet are rather thin, even if the surface temperature happens to be more favorable than on this one. This is so due to the fact that oceans on planets like that are too poor in terms of microelements that are vital for living creatures. Even taking into account meteorites that occasionally bombard the surfaces of these celestial bodies, the chemical diversity is simply not good enough for life to originate here. Still, studying ocean planets poses a great scientific interest. According to NASA's mathematical modeling estimates published in 2020, there may be billions of planets of this type in our galaxy, both cold, harboring an ocean under an ice shell, and warm, like Gliese 1214b. Water is one of the most widespread complex chemical compounds in the universe, and this means that the chances of discovering new ocean planets are quite optimistic. There is a giant cloud in space hundreds of light years away from the Earth, with some of its areas concealing dozens of yet unborn stars. Others are ripped apart by tremendous flashes. The space here is permeated by lethal ionizing radiation and threads of red-hot hydrogen, and fiery vortices are capable of absorbing whole stellar systems. This is where stars are born, the stellar nursery which is closest to the Earth. What does it conceal from us? There are stellar nurseries richly scattered across the galaxy, with some of them comparatively modest in size. Others stretch for tens and even hundreds of light years. These are vast nebulae made up of interstellar gas and dust being inexorably compressed by gravity forces. Most of these tremendous clouds are barely visible against the abyss of space, but some of them can be seen from the Earth with the naked eye. One of these structures is the Orion Nebula, located 1,344 light-years away from the Earth. It is the middle object in the so-called Sword of Orion, a clearly visible line produced by three relatively bright light sources. Due to its large size and comparative closeness to the Earth, the nebula has been attractive for scientists ever since the early days of astronomy. It is hardly surprising, therefore, that this great structure is one of the best-studied space objects. It was the Hubble Orbital Space Telescope that beamed back first images of the Orion Nebula back in 1993, where the rich diversity of its colors can be appreciated. Most of the material was of a reddish or bluish-purple hue, while unusual bright green lines of some peripheral areas were revealed by spectral analysis. This phenomenon perplexed scientists for a long time, as the observed radiation did not demonstrate any chemical element known at the time. There was even a hypothesis that was put forward about there being a hypothetical element nebulium, argued to be not present on our planet, but allegedly amply scattered across clouds and space. However, with the advancement of science, it turned out that the light was emitted by extremely rarefied and deionized oxygen. This discovery accounted not only for the bizarre illumination of many nebulae, including our Sun. There are currently not less than 3,000 stars discovered in the Orion Nebula to date, as well as giant clouds of interstellar gas and a great number of protostars. All this amazing diversity of space objects is concentrated in an area of around 23 light-years in diameter, all of them continuously and elaborately interacting with each other. The overall mass of the material concentrated here is around 10,000 solar masses. Looking at the Orion Nebula closer, we will notice several clearly defined areas. The most outstanding of them is Trapezium, also known as Theta 1 Orionis. It's an open star cluster about 300,000 years of age, made up of 8 main components. Some of them are binary stars, others have no companions. The brightest and most noticeable of the Trapezium's stars are 4 stellar systems designated by letters of the Latin alphabet. Located close to each other, they lie within an area about 1.5 light-years in diameter. Each of these objects' mass is within 15 to 40 solar masses, which means that these stars are quite young and hot. Theta 1 Orionis C is the most massive, as well as the brightest star in both the Trapezium cluster and actually the entire nebula. It is a white and blue main sequence star with a mass roughly 40 solar masses, whose radius is 8 times that of the Sun. The object's surface temperature is approximately 45,000 Kelvin, and its luminosity about 250,000 times higher than that of the Sun. The radiation of Theta 1 Orionis C illumines virtually all the nebula around it, but there is hardly any interstellar gas in its immediate vicinity. This is the case due to the fact it is typical for objects of this class to experience exceptionally powerful stellar wind that scatters rarefied material far off. Having traveled a few light-years away from Trapezium, we will see another remarkable system, which is Theta 2 Orionis. It is made up of 3 gravitationally bound stars located close to the so-called Orion bar, an extensive feature of hot gas emitting bright light. It was impossible to study this area for a long time on account of dense clouds of dust, and thanks to the James Webb telescope, more detailed images of this region have been beamed back to us. The first component of Theta 2 Orionis is just slightly less massive and not as luminous as the Trapezium's biggest star. As for its surface temperature, it measures about 35,000 Kelvin. The second component of the system is 15 times as massive as the Sun and 12,000 times as bright. The third component is as heavy as 5 solar masses, and its temperature almost reaches 14,000 Kelvin. However, it wasn't just bright stars that caught the researchers' attention. James Webb's infrared cameras allowed it to detect previously unseen objects, hidden deep within the clouds of gas and dust. Thanks to the telescope, about 180 so-called proplids have been discovered at the heart of the Orion Nebula. These are dense, dark protoplanetary disks surrounding stars that are still in the process of formation. One of these is Orion 294-606, a young protostar about 1 million years old, surrounded by a gas and dust disk about 300 astronomical units in diameter. Thanks to its being edge-on to Earth, we can observe its structure and size. It is expected to hit the main sequence phase in a few million years, and it will be accompanied by a system of several exoplanets and possibly their satellites. The night sky of these future celestial bodies must be a truly fantastic sight. Just imagine a multicolored luminous veil with the glow of a multitude of close and bright stars, far more numerous than those seen from the Earth, coming through. And now and then tremendous swirls of glowing gas cover half the sky, turning the night into translucent twilight. If we fly a little further and examine the wider region, we see that the bulk of the nebula is filled with scattered gas. The central part of the cloud is filled with highly ionized hydrogen, which actively absorbs high-energy stellar radiation. The temperature of this gas can reach 10,000 Kelvin, but it falls sharply towards the edge of the region. Temperature and pressure contrasts, as well as the collision of stellar wind streams, set material in space in motion, creating tremendous currents and vortices. According to calculations, some of them can reach speeds of up to 50 km per second, and their size can be greater than the solar system. Also, in some areas of the nebula, thin strands stretching for several light years have been detected, consisting of relatively cool molecular hydrogen, without mixtures of methane, ethane and water. Further out, we will see that the central region of the Orion Nebula is enveloped in a vast cloud of cooler, denser gas. The cloud of bright stars and the luminescence of ionized hydrogen intricately intertwine here, creating a beautiful multicolored curtain of light. Hidden behind it are hundreds of space objects, invisible in the optical range. But the infrared cameras of today's telescopes allow us to see through the veil of interstellar matter. By combining data from different sources, astronomers have discovered about 700 protostars at different stages of evolution within this region. Their concentration is noticeably lower than in the central part of the nebula due to the lower degree of gravitational compression of the interstellar gas. The absolute majority of these objects are very young by space standards and are still in the process of formation. According to modern concepts of stellar evolution, new stars form during gradual gravitational compression of large clouds of interstellar gas. Typically, as a result of this process, giant nebulae split up into a number of closely grouped gravity centers, which soon turn into protostars. Such clusters are called stellar nurseries, or more scientifically, regions of star formation. At a certain point, the internal pressure of the compressed gas compensates for the gravitational forces, bringing the protostar to a state of temporary equilibrium. The remaining material swirls into a giant vortex disk, with some of it gradually absorbed by the future star, and the rest of it, by contrast, expelled far beyond the boundaries of the nascent system. The growing magnetic field of the young star also plays its part. As ionized particles accelerate through its field lines and then rapidly escape from the vicinity of the object, it has been calculated that such flows can reach speeds of up to several hundred kilometers per second. As they collide with the gas clouds surrounding them, they create large-scale vortices and hemispheres called Herbig-Haro objects. In the process, part of the kinetic energy dissipates into light and heat, giving these bizarre structures different colors. In addition, the ultra-fast motion affects the surrounding material, spreading shockwaves across it, which incidentally are also captured by telescopes. Since stellar nurseries contain many closely spaced protostars, each producing several gas emissions, it is not surprising that Herbig-Haro objects exhibit an amazing variety of shapes and colors. Clearly, being essentially the result of a major cosmic collision, they are highly unstable and variable. Herbig-Haro objects rapidly change color and shape, and typically disperse completely over several tens of thousands of years. During this time, they cover between 1 and 3 light years on an escape trajectory from their parent stars. About 400 such objects have been discovered so far, with their total number within the Milky Way estimated to be about 150,000. Perhaps one of the varieties of this awe-inspiring natural phenomenon is the bullets, hundreds of astronomical units in diameter, also detected in the Orion Nebula. Moving at incredible speeds, they easily pierce thinner hydrogen clouds creating far-flung shockwaves in them. According to spectral analysis, the frontal parts of these objects contain atoms of iron that glow in the infrared. The bullets are estimated to be about 1,000 years old, and their origin is still a mystery. They supposedly originated from some catastrophic event. Moving on, we will soon find that the Orion Nebula is part of a much larger cosmic structure called the Orion Cloud. It stretches for hundreds of light years, accounting for virtually the entire constellation of Orion in the Earth's night sky. This is where the well-known Horsehead Nebula is located, remarkable for its bizarre shape. It is a dense dust cloud, about 3.5 light-years in diameter, clearly visible against a background of a contrasting scarlet glow. Also close to the Orion Nebula, there is an impressive cosmic structure called the Barnard's Loop. This emission nebula, about 300 light-years in size, came into being about 3 million years ago, after a series of consecutive explosions of mutually close supernovae. After the shock-compressed gas jets mixed together, they produced a gigantic curved nebula, and the glow of several young stars, gathered in an open cluster, made it reddish in hue. For all its beauty, the Orion Nebula is a fragile and unstable object by the universe's standards. Stellar winds and pressure of light from many young stars, as well as gas emissions and turbulent vortices, constantly disperse its material in the surrounding space. The nebula has already lost about 60% of its original material, and in about 100,000 years it will be stripped of its remnants. In place of the shining multicolored cloud, there will remain an open star cluster similar to the Pleiades. For a time, the young stars forming it will move together, but eventually each will find its separate way through the vast expanse of the boundless galaxy around. First stop is 202 light-years away from the Earth, destination K2-141, an orange dwarf. Its mass is roughly 0.7 that of the Sun, and its radius measures 68% that of our host star. With these parameters almost perfectly proportional, the star's temperature reaches 4,600 Kelvin, which is about 20% less than that of the Sun. And now to the planet in question. Just 0.007 astronomical units away from its star, there lies a really bizarre world, designation K2-141b. This rocky exoplanet is 5 times as massive as the Earth, with its radius 1.5 times as big as that of our Earth. All this gives us grounds to assume that the gravity on the planet's surface is at least twice as strong as that on our planet. The heavy metallic core, meanwhile, accounts for 20 to 50% of the planet's overall mass. It takes the celestial body about 6.5 hours to complete a full orbit around its parent star. Being extremely close, it is tidally locked to it. That is, it faces the star with one and the same side at all times. Observations show that the temperature on the planet's day side reaches 3,270 Kelvin or 3,000 degrees Celsius. This is enough not only to melt most rocks and metals, but also to effectively evaporate them. The day side of the planet is assumed to be covered with a lava ocean that never ceases to boil. The atmosphere is thought to be rather exotic, made up of steams of heavy metals and silicates. By contrast, the planet's night side is incredibly freezing. According to estimates, the temperature of most of its area is tens of times lower than that on the day side, and on balance, its values are supposed to be sub-zero. Mathematical modeling shows that this sharp temperature contrast gives rise to exceptionally strong winds whose speed reaches 1.75 kilometers per second. This is roughly 5 times the speed of sound, which means that the surface of K2-141b is continuously shaken by exceptionally powerful, deafening rumbling. It is assumed that on reaching the night side, atmospheric streams condense and precipitate on its surface in the form of fiery rain. This forms lava rivers, and eventually this molten metal makes its way back into a magma ocean to evaporate again later on and to continue this incredible fiery circulation. However, this infernal cycle affects only a relatively small part of the planet's night side. The thing is that masses of evaporated elements from the day side simply don't make it to the main part of the night side and precipitate somewhere on the border. That is why the central part of the night side is likely to be a freezing desert bound with layers of solid rocks. Remarkably, K2-141b is far from being the hottest planet that we know of. For example, there is an object referred to as Kelt 9b lying 670 light-years away from the Earth. Its surface is as hot as 4,600 Kelvin, which is approximately 4,330 degrees Celsius. Just to compare, the outer layers of almost all red dwarfs, for example, are much cooler, which means that in terms of temperature, this exoplanet is quite a match to stars. Its parent star, designation Kelt 9, is of a whitish-blue color and has a mass 2.6 times that of the Sun. As for its diameter, it is 2.3 times that of our star. The surface temperature of Kelt 9 is rather high at approximately 10,170 Kelvin, or a staggering 9,900 degrees Celsius. This largely accounts for the extreme conditions on Kelt 9b, which lies quite close by. Just 0.035 astronomical units away from its parent star, the planet completes a full orbit around its system's center roughly every 1.5 days. Kelt 9b is a hot gas giant. Compared to Jupiter, its mass is 2.8 times as big and its radius measures roughly twice as much as that of the largest planet in our system. Based on today's notions about the composition of this type of planets, the inner part of Kelt 9b's atmosphere is supposed to be even hotter. Estimates allow for this value to reach as much as 11,000 Kelvin on account of heavy metal ionization. With this figure so exceptionally big, it appears that the planet's atmosphere should contain vaporized iron and titanium, alongside the elements we're used to in an atmosphere's composition such as hydrogen or helium. Its close proximity to the parent star and the extremely high temperature cause the planet to gradually lose its atmosphere. By and by, powerful stellar wind blows it off into space, which is why the object is shrouded in a cloud of rarefied gas. This material will eventually be attracted and absorbed by the star. Interestingly, according to some estimates, the exoplanet loses up to 68 Earth masses every billion years. Theoretically, in a long while, Kelt 9b may well get stripped of all of its atmosphere and transform itself into a Chthonian planet. However, its parent star is likely to hit the final stage of its life cycle long before that, swallowing up and destroying all the celestial objects within its reach. The space objects we have just looked at are a living proof, as it were, of the fact that stars can destroy the planets close to them and not just warm them up. But incidentally, there are celestial objects out there in the universe that have experienced their parent star's wrath in full measure. One of such objects lies 4,570 light-years away from the Earth in the environs of a small star, designation V391 Pegasi. Now, the star is a white dwarf whose mass is twice as little as that of the Sun and whose radius is approximately 23% that of our parent star. The temperature of this celestial object is unbelievably high, at almost 30,000 Kelvin. All thermonuclear reactions in its interior would have run their course a long while ago. Up ahead are hundreds of billions of years of slow cooling, with the white dwarf eventually transforming into a black one. The planet we will look at, referred to as V391 Pegasi b, is in this ordinary star's environs. Its lot is exceptionally amazing. According to mathematical modeling, the planet not only survived its progenitor star shedding its outer layers, but actually found itself almost within the star for some time. It is assumed that when the system's star V391 Pegasi transformed into a red giant, its outer layers, extremely rarefied by then, were almost brushing the planet's orbit. Their density became dozens of times lower than the atmospheric air we're used to, which means that the celestial objects devoured by the dying star remained whole for a while and didn't get destroyed at once. It goes without saying that they would have been losing their speed and dropped into the star's hotter and denser layers. Still, V391 Pegasi shed its outer layers sooner than V391 Pegasi b melted and ceased to exist as a whole object. At the moment, the exoplanet appears to be a gas giant, 3 times as massive as Jupiter. Its orbit passes 1.7 astronomical units away from its parent star, and it takes the planet approximately 1,170 Earth days to complete a full orbit around its system center. It is still not entirely clear how this astronomical body managed to preserve such a big mass after its collision with the scorching hot layers of the star. Their influence was supposed to have destroyed the object's atmosphere completely. However, there is no doubt that the host star's collapse brought about some dramatic changes, both in terms of the exoplanet's orbit and its parameters. That is why it is hardly possible for us to ever find out what V391 Pegasi b was like before immersing in a sea of raging plasma. Space expanses conceal uncountable astronomical objects with the most bizarre properties. Some of them are almost totally invisible through regular telescopes, but can be detected by looking at radio wavelengths when exploring space. An example of such like celestial objects is pulsars, neutron stars spinning on their axes at a mind-boggling speed. These object spectra are peculiar for exceptionally fast and regular pulsations. That is why it is quite easy to detect another celestial body transiting between a radiation source like that and an observer on the Earth. This is precisely the way our next object of interest was discovered. But first we'll be looking at a pulsar which lies around 4,000 light-years away from the Earth. This neutron star boasts quite a long name. Here it is on the screen. And now let's check out its remarkable features. The pulsar's diameter is just a measly 20 kilometers, and its mass is approximately 1.4 that of the Sun. The object spins at an incredible rate, with roughly 10,000 rotations a minute, while continuously emitting powerful electromagnetic radiation impulses. Now the surface of the exoplanet, our next object of interest, is continuously exposed to these waves of lethal radiation, which makes it a hostile and forbidding place. It takes this planet just 2 hours to complete a full orbit around its system's center, and the distance to the pulsar is smaller than the Sun's radius, just 600,000 kilometers or 0.004 astronomical units. Incidentally, the celestial body's surface is bound by eternal cold and space as its parent star just barely emits thermal energy. The object's mass is around 330 that of the Earth, while its radius is 4 times that of our planet. This makes gravity on its surface as much as 20 times stronger than on the Earth. Estimates show the planet's average density to be about 23 grams per cubic centimeter, which is more than most chemical compounds we know. The planet is thought to be made up for the most part of crystallized carbon under a lot of pressure. Besides, the object's upper layers contain some oxygen, which is probably chemically bound with carbon. It is highly doubtful that a celestial body located so close to a star could possibly have survived a supernova event. It is more realistic to assume that the exoplanet formed after the progenitor star had come to the end of its life cycle and had transformed itself into a pulsar. The exoplanet could be a piece of debris left over from a white dwarf whose material would have dispersed for the most part. This makes classifying the exoplanet an especially difficult task. Still, whatever it is, this world remains one of the most dangerous and hostile ones lurking in the depths of the cosmos. "650 light-years away from the Earth, there lies IRC plus 10-16, a majestic star also known as CW Leonis. Its radius at its pulsation peak may reach 560 times that of the Sun, which is about 2.6 times the distance from the Earth to our parent star. With CW Leonis hypothetically placed in the middle of our system, all the planets as far as Mars would find themselves under its surface, which would even brush the inner boundary of the asteroid belt. Incidentally, the star's mass is not that great, roughly 1.5 to 4 solar masses. Its surface temperature is just 2300 Kelvin or about 2000 degrees Celsius. But due to its impressive dimensions, the star emits on average 8,500 times more energy than our Sun. Like any other red giant, CW Leonis is in its final life stage. Its age hasn't been defined precisely, but it is estimated to be several billion years. It is assumed that in its salad days, CW Leonis was a white-blue star with a mass 3 to 5 times that of the Sun. However, by 1 billion years ago, a great part of the celestial body's hydrogen had burned out and transformed into helium. Slowly settling in the star's center, the helium ousted all the remaining hydrogen and formed a scorching hot core which did not participate in any thermonuclear reactions. This process, typical for all stars whose mass is close to that of the Sun, is the starting point for a star's transformation into a red giant. The star's inner pressure causes it to expand to great proportions, which renders the outer layers more rarefied and unstable. The space object's diameter grows to be dozens of times greater, with its color gradually assuming a blood-red hue. A thermonuclear reaction still takes place in the star's depths, which causes the pressure and temperature of the stellar plasma to increase. At a certain point, this unleashes a chain reaction of nuclear fusion, where helium nuclei are transformed into carbon. This is the so-called helium flash. It is a complex, multi-level physical process that dramatically transforms the star's inner structure. With its core incredibly heating up, its outer layers, on the contrary, cool off and darken. There are currently great amounts of carbon in CW Leonis, but its mass is insufficient to hit the next level of nucleosynthesis. As a result, the thermonuclear combustion in the object's interior becomes unstable. The stellar matter gradually cools off and shrinks under the influence of gravitation. This heats up the star's interior again, and the reaction is unleashed with a new force. After receiving a new portion of thermal energy, the stellar matter expands again, and the combustion dies down. It is assumed that this cyclic process underlies the occasional changes of the star's luminosity. CW Leonis has a 649-day pulsation cycle, and with the luminosity at its peak is 11,300 times brighter than the Sun. With the luminosity at its lowest, meanwhile, the object emits 6,250 times more energy than the Sun. At the moment of contraction, the upper layers of stellar matter partly detach themselves from the star. This forms a carbon-oxygen gas nebula that the star is enveloped in. According to some estimates, CW Leonis loses 4 times 10 to the power of 22 tons of material every year on account of this process, and amount approximately 7 times the mass of the Earth. Observations show that the circumstellar nebula is not less than 69,000 years old, and its mass is about 1.5 times that of the Sun. As for its size, it reaches 84,000 astronomical units. The nebula has an elaborate structure with bulges and pockets of gas, as well as half-arcs and irregular rings. It is posited that these formations appeared due to magnetic activity and stellar wind generated by the unstable star close by. The chemical composition of the cloud CW Leonis is shrouded in is of great interest to explorers. Spectral analysis data reveals it to contain around 70 different chemical compounds, for example carbon dioxide, water and ammonia, to name but a few. There are also quite a lot of elements from the upper part of Mendeleev's periodic table, right down to iron. CW Leonis may have had planets in the past, but they appear to have been swallowed up early on at the stage of expansion. In any event, years of observations did not reveal distinct traces of their existence in the past. What was registered was subtle changes in the star's orbit back in 1994, and more recently in 2017, mysterious shifts of matter were detected in the cloud of gas and dust enveloping the star. Some small red dwarf orbiting the giant could well account for these phenomena, although attempts to detect its radiation have so far been unsuccessful. This could be due to the nebula close by, which disperses and reflects the energy flow from sources of light located nearby. This phenomenon camouflages any objects in the immediate environs and prevents them from being accurately recognized. The mass of CW Leonis's hypothetical stellar companion is assumed to be definitely smaller than that of the Sun, and it should take it approximately 100 years to complete a full orbit around the giant. Another outstanding feature is a comparatively high water content in the star's environs and envelope. At first, it was posited that the star would melt and swallow up icy comets as it expanded. However, observations carried out in 2009 showed the temperature of some spectral lines to reach 1000 Kelvin, which is possible only on condition that water vapor forms actually in the upper layers of the giant. This fact did not fit in the model of red giant's structure accepted at the time, according to which all oxygen in stellar matter necessary for water synthesis must be used up completely to produce carbon monoxide. A new hypothesis was put forward to account for the witnessed phenomena, which stated that molecules of silicon oxides and carbon are destroyed by a powerful ultraviolet radiation. After that, the released oxygen reacts with hydrogen and there forms scorching hot water vapor. The weakness of this hypothesis is in the failure to account for the source of ultraviolet radiation. Reactions like that may occur only in rather high temperatures, that is, within stellar matter. However, it is practically impervious to cosmic rays. This paradox may be explained by yet another assumption. Since the star is unstable, large ruptures and low-density areas occasionally occur on its surface, where ultraviolet radiation is not blocked out that effectively. The water vapor's overall mass in the star's atmosphere and outer layers is estimated at several quintillion tons. Enormous though this figure may seem, in fact, water accounts for just around a billionth of the star's overall mass. According to today's notions of stellar evolution, being a red giant, CW Leonis is in its autumn years now. It will deplete its stellar fuel in the next 10 to 30,000 years, after which it will discard its outer layers following a powerful explosion. It will transform into an incredibly hot and dense space object, a white dwarf. Its mass will be roughly 80% that of the Sun, and its temperature will reach several million degrees in the first seconds after the transformation. However, with no energy source, it is destined to slowly and irrevocably fade in the course of billions of years to follow. Eventually, the celestial body will be almost invisible against a background of cosmic emptiness when it becomes a mysterious black dwarf. But this will not happen anytime soon. The shockwave and the mind-boggling temperature in the epicenter will generate new elements that are not to be found in a star's interior. For example, uranium, gold and lead. They will later become part of new celestial objects. Millions of years later yet, radioactive decay will heat the planet's interiors, melt the ice, and saturate the oceans with microelements, thus creating conditions for the genesis of life. The universe is constantly evolving, and global cataclysms and destruction are an inalienable part of this process. But at the end of every storm, there are fresh rays of light. Temperatures of any star's interiors are incredibly high. It is hardly surprising, as thermonuclear synthesis, that is the main energy source of all stars, can take place only in these extreme conditions. When two atoms of hydrogen merge, they produce an atom of helium and release an electron and several neutrinos. In addition, a great amount of energy is released during the process. Still, the hydrogen-helium synthesis isn't the only process that heats up stars. At higher temperatures, other elements may take part in chemical reactions as well, for example lithium, carbon or oxygen. In this case, cores of heavier elements are produced, such as sulfur, magnesium or phosphorus. Their charge is higher and they repel each other more robustly. Much more energy is needed to overcome this resistance. When a main sequence star depletes most of its hydrogen supply, it starts to expand and cool off. With time, it ends up as a red giant. It will continue to burn due to thermonuclear reactions of helium transforming into carbon and oxygen. The lighter the star, however, the less time it will continue to burn. Eventually becoming unstable, it sheds its outer layers and goes supernova. This leaves it a white dwarf with no resources to fuel any thermonuclear reactions anymore. With all its energy sources depleted, it is forced to gradually cool off. Interestingly, when the mass of a star is higher than a certain value, heavy thermonuclear synthesis may become the star's main energy source even after all hydrogen has been used up. Such celestial objects are referred to as Wolf-Rayet stars. This class of space objects was discovered back in 1867 by the French astronomers Charles Wolf and Georges Rayet. The scientists' attention was caught by anomalously bright emission lines of heavy elements in these stars' spectra. As for the inner makeup of these unusual celestial objects, it was accounted for much later. Stars of this class are generally heavy. They have quite a meager supply of hydrogen and are in the final stages of their evolution. Wolf-Rayet stars are extremely rare. To date, just a few hundred of them have been discovered in our galaxy. As for their overall count in the Milky Way, it is estimated that there can't be over 2,000 celestial objects of this class. Wolf-Rayet stars are subdivided into three main sequences depending on the prevalent element in the spectrum: nitrogen, carbon and oxygen sequences. Each of them, in its turn, is subdivided into several types. As for the hottest star in the studied universe, it falls into the category of the oxygen spectral sequence ones. The celestial body, which is now known as WR102, was discovered back in 1971. At first, it was mistaken for the optical counterpart of the X-ray source GX3+1. However, further observations revealed that there were two completely different objects. According to data acquired thanks to spectral analysis, the discovered star had unusually bright oxygen lines in its radiation spectrum. Thus, in 1982, WR102 and four more bright stars became the first to form a new class. Spectral analysis showed that the star's surface temperature reaches over 210,000 Kelvin. This makes WR102 approximately 36 times as hot as our Sun. The luminosity of this scorching hot object is unbelievable. It is estimated at over 380,000 times that of the Sun. WR102 lies about 10,000 light-years away. The star is located in the part of the sky with the constellation Sagittarius. Incidentally, in spite of its exceptionally high luminosity, it can't be seen with the naked eye, as it is too far away from us. WR102 currently belongs to the extremely rare star class WO2. Containing great amounts of oxygen and almost no hydrogen, it mainly relies on the merging of heavy cores of such elements as neon, carbon and oxygen as its sources of energy. To date, only 9 objects of this class have been discovered, with 4 of them located in the Milky Way and the other 5 in other galaxies. There are two factors that make oxygen spectral sequence stars rare. Firstly, there are very few of Wolf-Rayet stars around because only stars with a mass not less than 40 solar masses are potential candidates to become ones. Secondly, this class represents the final stage of evolution of stars of this type. The stage may last anything from 1,000 to 10,000 years, which is mere seconds in astronomical terms. Being of comparatively modest dimensions, WR102 is notably quite a dense star. With its radius measuring just 58% that of the Sun, its mass, on the other hand, is estimated at 15 to 18 solar masses. On its birth, it is thought to have been as heavy as 40 to 60 solar masses. Still, the high temperature and robust chemical reactions in the star's interior cause an exceptionally powerful stellar wind, whose particles' velocity is over 5,000 kilometers per second. It takes WR102 just a few months to lose 1 Earth mass worth of material on account of its stellar wind. At this rate of particle emission, the star is going to lose 1 Sun mass worth of material in the course of 10,000 years. There are no planets orbiting WR102, but it is shrouded in a gas envelope. Not dense and exposed to powerful ultraviolet radiation and strong stellar wind, the envelope gets contracted and ionized, which sustains its elaborate structure of protuberances and arches all around the star. According to a proposed theory, the gas cloud around WR102 may probably be remnants of the former hydrogen outer layer of the star. Another theory maintains that the cloud came to be as a result of the particle flow emitted by the star. WR102 is not the only outstandingly blistering place in the universe. For example, WR142, WR30A and WR93b, as well as the central star in the Bug Nebula NGC 6302, are as hot as around 200,000 Kelvin. Some white dwarfs may have almost the same surface temperature. However, all these are no match to neutron stars. When neutron stars are born, their temperatures may reach a staggering 100 billion Kelvin. Active neutrino emissions cool them off comparatively rapidly. But either way, the surface temperature of any neutron star is never less than a few 100,000 Kelvin. As for their cores, they must, admittedly, be hotter still. Having said that, it is highly improbable that the ultimate temperature record is ever going to be beaten. According to today's cosmological concepts, the temperature of the universe at the moment of the hypothetical Big Bang was approximately 1.4 times 10 to the power of 32 Kelvin. A fundamental physical constant, this value is referred to as the Planck temperature. Contemporary physics is not capable of defining a substance of a higher temperature, as physical laws are distorted beyond any recognition in such incredibly harsh conditions, quite beyond our imagination. Getting back to WR102, judging by the data we have on stellar evolution today, this star is in its autumn years now. As opposed to main sequence stars, Wolf-Rayet stars do not expand in their final stages of life. Their substantial mass holds all the star's material together in a dense and hot ball. However, after losing a lot of its mass through stellar wind, the object will eventually get destabilized. If current estimates are accurate, WR102 appears to be ready to go supernova at any point in the next 1,500 years. Bearing in mind that the distance between the star and the Earth is 10,000 light-years, it is highly likely that the event has already taken place. A supernova would have been accompanied by an extra-powerful gamma-ray flare. Fortunately, our planet is too far away to suffer any pernicious effects of this dangerous emission. WR102 is comprised of rather heavy chemical elements and even iron. Its later evolution will force it to contract to a critical point. The great explosion bringing the star's life cycle to a close will unleash processes of robust proton and neutron capture. This way, still heavier elements form, including transuranium ones. Eventually, WR102 will be replaced by a neutron star, a celestial body unbelievably hot and dense. The former star's outer layers, disrupted by the explosion, will form a nebula. Slowly cooling off, it will give off heat to the space around it. Many billions of years later, this material will be able to form a new planetary system. Until a short time ago, it was UY Scuti that used to be considered the largest star known to mankind for a long while. Located 9,500 light-years away from the Sun, the star is so staggeringly enormous that it would cover areas beyond Jupiter's orbit were it placed in the center of the solar system. Its radius may reach 1,900 those of the Sun, and its volume may be over 5 billion times that of the Sun. However, recently a new giant has claimed the title of the largest star in the known universe. It is known as Stephenson 2-18 or RSGC 2-18. The star lies approximately 20,000 light-years away from the Sun and is part of the open cluster Stephenson 2, although according to some scientists, this space object should not be associated with the Stephenson cluster, as it wouldn't be accurate. Either way, Stephenson 2-18 is located in the Scutum constellation and continues to bear its original name. The star itself was catalogued in the All-Sky database back in the 1990s, but giant clouds of cosmic dust largely interfered with observation of the star clusters in the Scutum constellation, obscuring them from any observer anxious to find out more. Only in 2020 were scientists able to acquire data about its size, and the information proved to be astonishing. According to some estimates, the radius of Stephenson 2-18 may reach up to 1.5 billion kilometers, which is 10 times the distance from our Earth to the Sun, or 2,150 times the radius of the Sun. This means that the supergiant's volume should be about 10 billion times that of the Sun. Placed in the center of the solar system, Stephenson 2-18 would easily swallow up Saturn, along with all of its rings and moons, to say nothing of the terrestrial planets. Interestingly, it would take light almost 8.5 hours to travel the length of this gigantic star's equator. This is the same time it takes sunlight to reach Pluto at the remotest point of its orbit. The supergiant's luminosity is estimated to reach 440,000 times that of the Sun, although its surface temperature is comparatively low at about 3,200 Kelvin. This is about 2 times as little as that of the Sun and corresponds to the red band of the light spectrum. This is the reason why Stephenson 2-18 falls into the category of red supergiants. Also, this relatively low temperature implies that most of the star's radiation is in the visible and thermal spectra, with amounts of deathly ultraviolet and X-ray types of radiation rather negligible in comparison. It may seem strange that in spite of its impressive dimensions and sufficient luminosity, Stephenson 2-18 cannot be seen from the Earth with the naked eye. But this has to do with its low surface temperature as well as clouds of stardust and gas shrouding the giant star, thus concealing it from observers on our Earth. They absorb and disperse the star's light, and this poses difficulties for studying the object. The mass of Stephenson 2-18 still remains to be gauged. However, supposing its inner makeup is similar to that of UY Scuti and other supergiants, it should be anything within 20 solar masses. If it is the case, the average density of supergiants like that must be extremely low and almost equal to the density of the Earth's atmosphere at a height of about 90 kilometers above the sea level. That is practically on the border with space. It is really amazing that thermonuclear energy, that is the kind of energy that gives a glow to a star, is still sustained in such conditions. Supergiant sizes are so mind-boggling that these objects are hardly steady. Most of them are variable in terms of their luminosity, and as a rule this variability is unpredictable. No wonder, as the overwhelming majority of supergiants are in the final stages of their life cycles. which means that they may go supernova literally at any moment. According to the contemporary scientific concepts of stellar evolution, it is stars with original masses from 10 to 40 that of the Sun that qualify to become red supergiants at a later stage of their existence. Thermonuclear reactions in their interior rapidly burn out all hydrogen, thus turning it into helium. After that, fusion reactions of helium, carbon, oxygen and lithium become the chief energy source of the star. Life expectancy of stars of this kind is comparatively short, just a few million years. As it evolves, the prospective supergiant rapidly expands in size and loses its mass on account of strong solar wind. Clouds of stardust and gas surrounding the original star are quickly absorbed by the new star, which keeps swelling way beyond its original size at an astonishing rate. However, its own solar wind creates a new nebula around the star. On account of the short lifespan of this kind of star, no planets can realistically originate in this nebula. Eventually, the supergiant explodes. Following the supernova or even hypernova event, the outer layers of the star are hurled away and then gradually cool off, forming a nebula. As for the former core, it becomes either a neutron star or a black hole depending on its mass. By the way, feel free to see our previous videos about dwarf stars and supernovae. A hypernova event is accompanied by a high-energy X-ray burst, powerful enough to eliminate any life within the radius of several light-years. Luckily for us and the Earth, all supergiants identified by scientists so far lie considerably further than that, so we seem to be safe from those. Due to active radiation of charged particles, the rotation of stars of this type gradually slows down, and eventually their outer layers practically grind to a halt. The core of the star, meanwhile, continues to rotate quite unabated, and there may be a substantial difference between the speed of the core and that of the outer layer. Taking into consideration the high luminosity, low temperature and impressive dimensions, on balance, it is safe to assume that the habitable zone of Stephenson 2-18 should be really huge. Its middle should lie approximately 663 astronomical units away from the star's center. In other words, 20 times the distance from the center of the Sun to Pluto's orbit. And as for the area of the habitable zone, it is expected to be 1 billion times that of the Sun. Scientists do admit of the possibility of the existence of planetary systems around supergiants. But what with these stars' short lifespan and unstable conditions, the chances are almost negligible. At any rate, no confirmed exoplanets have so far been discovered in the environs of one. Stephenson 2-18 lies so far away that its light travels to our Earth for 20,000 years. For all we know, at this very moment its core might be shrinking to form an extremely dense neutron star, with red-hot shards of outer layers flying away in all directions to become part of ice-cold space. But mankind will be able to find this out only in a very distant future. Long before telescopes had been invented, people could observe a light strip crossing the heavens. The fascinating and mysterious phenomenon prompted a multitude of legends, but it took thousands of years of scientific progress to finally account for it. It turned out that the Milky Way wasn't a path of gods. What it is the dissipated light of billions of stars too remote to distinguish each one separately. The idea of the stars around us making up part of a single structure of enormous dimensions was first suggested by Immanuel Kant back in 1755. He also assumed that some nebulae discovered by scientists could in fact be remote star clusters, that is, other galaxies. This ingenious guess was well ahead of its time, with the philosopher's contemporaries initially dismissing it. Only in the early 20th century did the progress of observation equipment enable scientists to confirm the existence of other galaxies, and in 1936, Edwin Hubble devised a classification system. Many of its principles are still referred to by scientists today. According to this system, the Milky Way falls into the category of barred spiral galaxies, although it took a long while before it had assumed its today's looks. Our galaxy is quite an old one, since the stars in its central globular clusters were born as far back as around 13 billion years ago. At the same time, there are some areas in the Milky Way where stars are actively born, which means that there is always a fresh supply of young stars. The collected data points to the fact that the Milky Way is a comparatively large galaxy in astronomical terms. The diameter of its disk measures as much as 200,000 light-years, with a halo reaching out into space much deeper yet. Our galaxy is home to at least 200 billion various stars, as well as 25 to 100 billion brown dwarfs. In addition, it contains over 1 trillion planets, countless small celestial objects, as well as clouds of cosmic dust and interstellar gas, which may reach gigantic dimensions. At the same time, regular matter accounts for a small ratio in the galaxy. Around 90% of the Milky Way's overall mass is the so-called dark matter. The amount of light emitted by this mysterious and widespread substance is negligible. However, dark matter plays an active role in gravitational interaction. Even though most of the galactic mass remains invisible, we can still calculate it. To that end, scientists refer to stars' trajectories of movement around the center of the Milky Way. According to the estimates, the overall mass of our galaxy reaches 0.8 to 1.5 trillion solar masses. The structure of the Milky Way is quite elaborate. We'll start our journey today from its center. This area of the galaxy is shrouded in massive clouds of gas and dust, but by happy chance we can observe it through the so-called Bardes window, an area of space with lower amounts of dust. Just like most spiral galaxies, the Milky Way has a supermassive black hole in its center, which is surrounded with an accretion disk with a radius roughly 3 light-years. Dubbed Sagittarius A star, it is the closest object of this class to us. Its mass is 4.3 million solar masses, and its radius isn't over 16 million kilometers, which is 3 times smaller than Mercury's orbit. The first data about the nature of the object in the center of our galaxy was acquired in the course of long observations and thorough calculations. Only as recently as on May 12, 2022 was it possible to get the first image with the help of the EHT network of radio telescopes, and so the earlier hypotheses were confirmed. The area in the center of our galaxy is highly populated. More than 6,000 stars have already been detected within 3 light-years from the black hole, with the orbits of some of them defined rather accurately. For example, there is a white-blue star, designation S62, which is 17.8 astronomical units away from the black hole on its closest approach to it, while moving at 6.7% the speed of light. Classical mechanics laws are inadequate for description of the trajectory of movement of a star as swift as that because of relativistic effects. Just to illustrate, the axis of its orbit shifts by 75 angular minutes with every completed orbit. Besides, when crossing this area in space, we can see several large star clusters with a total mass of around 1 million solar masses. And slightly further, roughly 200 light-years away, another massive black hole is likely to be lurking, whose mass should be around 100,000 times that of the Sun. Traveling further on, we will reach the central molecular cloud, an irregularly shaped area measuring 1600 to 1900 light-years, whose mass is over 60 million solar masses. There are a great many stellar nurseries and gas nebulae, as well as protostars and remnants of supernovae. Most of the cloud's matter is dense hydrogen, whose temperature fluctuates between 50 and 600 Kelvin, which corresponds to 223 degrees Celsius below zero to 327 degrees Celsius above zero. Spectral analysis shows the gigantic nebula to contain carbon monoxide, methyl alcohol, and hydrocyanic acid in addition to hydrogen. Having receded from the Milky Way's center a bit, we will see that it is encompassed by a bulge, a bright and massive formation of an elliptical shape. With its length reaching 10,000 light-years, its transverse diameter is roughly 7 light-years. The total mass of the bulge is as much as 10 billion times that of the Sun. The exact number of the stars cannot be calculated because their radiation blends and renders any estimates unrealistic. Being elongated, the bulge forms the so-called bar stretching for approximately 13,000 light-years and serving as the base for spiral galactic arms. It is here, at one of its ends, that we can see the star cluster Stephenson 2, containing the largest known star today. Its designation is Stephenson 2-18, and its radius is 2,150 times that of the Sun. Unfortunately, chances of finding exoplanets orbiting this outstanding object are quite minuscule. Even if planets did exist at some point in the past, the hypergiant would have swallowed them up while it was expanding. The galaxy's center is home to billions of stars and apparently a great number of exoplanets. Chances of encountering a potentially habitable world among this great multitude are much lower than in less populated areas of the galaxy. This is due to the fact that when a big number of stars are located close together, they destabilize exoplanets' orbits, while their powerful radiation is lethal to all living things. That is why a special area in the galaxy is defined as the habitable zone. It looks like a ring, with a radius measuring 22 to 29,000 light-years, and contains star systems with the most favorable conditions for the genesis of biological life. Worlds encompassed by the ring languish in exposure to excessive radiation, while beyond the ring there's a lack of heavy elements. However, mathematical modeling shows that stars within galaxies are able to migrate thousands of light-years away, thus either leaving the habitable zone or entering it. Consequently, with an exoplanet lying within the zone, it does not automatically suggest favorable conditions on it. Moving on away from the center of the Milky Way, we will have a chance to check out its most impressive part, the galactic disk. It is made up of two components with different properties. The first one, known as the thin disk, measures 1,000 to 1,300 light-years in thickness, and its visible radius measures as much as 50,000 light-years. On the edge, it gradually dissipates, with the outermost stars lying up to 100,000 light-years away from the galaxy's center. This part of the Milky Way contains around 80% of the galaxy's visible mass, and in fact, it was the last component to have formed. As for the thick disk, its diameter is comparable to that of the thin disk, but it's 4 times as thick and is much more rarefied. It is made up of old stars and is practically devoid of interstellar gas. Observations of some stars in the Milky Way, as well as mathematical modeling, show our galaxy to have swallowed up another one in the period from 11 to 8 billion years ago. This hypothetical cosmic structure was dubbed Gaia Enceladus. It is thought that it contributed several billion stars to the Milky Way, as well as great amounts of interstellar gas and dark matter. It is thanks to this tremendous event that most of our galaxy's thick disk formed, and an additional supply of gas led to a stellar baby boom. There is no doubt that spiral arms are the most noticeable structural elements of our galaxy's disk. Usually 2 major ones are singled out, the Scutum Centaurus arm and the Perseus arm, and 2 minor ones, the Norma arm and the Carina Sagittarius arm. Sometimes a 5th large arm is taken into account, named after the Cygnus constellation. Galactic arms are areas of especially high star count. Most of interstellar gas is also concentrated here, which is why the rate of star formation in the arms is 3 to 5 times higher than in the galaxy on average. They spend the first millions of their lives in open clusters, but gravity forces are too weak to hold the stars close together for a long time. This destabilizes the clusters, and young stars gradually drift away from each other. Traveling along the Carina Sagittarius arm, we will reach a fork that links it to the Perseus arm. The length of this stellar structure reaches 11,000 light-years, and its width measures roughly 3,500 light-years. It is referred to as the Orion Arm, and it is here, 27,000 light-years away from the galaxy's center, that the solar system is located. From our planet's perspective, the galaxy's center is seen as a dark abyss. This is the Great Rift, an area of space that shuts out the greater part of the Milky Way from our gaze. It is filled with massive clouds of interstellar gas and dust, and its total mass is as much as 1,000,000 times that of the Sun. Even though the Great Rift is practically not transparent in the optical range, its matter actively emits radio waves and thermal energy. Spectral analysis data reveals that the clouds are mostly made up of hydrogen with a small percentage of more complex compounds, ammonia, alcohols and amino acids. The Great Rift is thought to be a potential stellar nursery, but it is going to take a while until the first stars light up in that area. While it is still not quite active, let's move on, beyond the galaxy disk. Even though its bright and clearly defined arms attract a lot of attention, there is more to the Milky Way than that. If we look closer, we will see the vastest and the most rarefied of its components, the halo. Its visible part, spherical in shape, stretches for up to 260,000 light-years away from the galaxy's center, but accounts for just a few % of the total mass. The halo contains a great number of globular clusters made up of remarkably old stars over 12 billion years of age and several tremendous stellar streams. The Sagittarius stream, for example, made up of several thousand stars, encompasses our galaxy in an elongated ellipsis, which is almost perpendicular to the main plane. Modeling shows that all these stars are highly likely to have been gravitationally captured by the Milky Way from a dwarf satellite galaxy, designation Sagittarius DEG. It lies 500,000 light-years away from the Milky Way's center and is going to be swallowed up by it completely within several billion years. Another dwarf galaxy has already met a similar fate. Lying in the Canis Major constellation, it was almost destroyed by the Milky Way, which pulled out millions of its stars by gravity forces. Stretching for 200,000 light-years and mixing with other stars, this string of stars with a total mass of roughly 100 million solar masses has already wrapped around our galaxy 3 times. Apart from bright but rare stars and clusters, the halo contains great amounts of gas, whose temperature reaches millions of Kelvin. Also, great amounts of dark matter are thought to be scattered in the vicinity of the Milky Way, forming the so-called dark halo. Stretching for up to 2 million light-years, it hardly emits any electromagnetic radiation and can be detected only by gravitational interaction. The dark halo remains an unsolved mystery, yet it greatly contributes to the global stability of our galaxy. Distances from the Milky Way to other galaxies are by all accounts mind-boggling. As a rule, it is anything from millions to billions of light-years. Due to the universe's cosmological expansion, the distance between the Earth and any remote object in the universe is constantly growing, which makes the light emanating from this object look redder than it actually is. This phenomenon is known as a redshift. It is of great help in gauging distances and velocities on the astronomical scale. Alternatively, some galaxies' spectrum is blue-shifted, which means that they are not on an escape trajectory from us, but on the contrary are moving to meet us. One of these unusual space objects is the galaxy M86 in the Virgo cluster. Roughly 52 million light-years away from the Sun, it is moving towards the Milky Way at a speed of around 244 km per second, which makes it one of the fastest-moving blue-shifted galaxies. By moving at a high speed through the scattered gas the Virgo cluster is filled with, M86 is constantly shedding its own interstellar matter. As a result of this process, it leaves a trail of long lines of warm ionized hydrogen behind. M86 is connected with the almost destroyed spiral galaxy NGC 4438 with several of these filaments. These two galaxies are thought to have collided at some point in the distant past, which was the smaller one's undoing. Interestingly, M86 is known to have destroyed its other neighbors in the past as well. Several stellar streams have been detected in its halo that are likely to be the remains of smaller galaxies absorbed earlier. An impressive number of globular clusters in its structure is another outstanding feature of M86. Observations show that their number is upwards of 3,800, which is around 25 times as many as in the Milky Way. There is a theory that claims these clusters to be the remains of dwarf galaxies that M86 would have absorbed in the past. If it really is the case, then it would have destroyed tens or even hundreds of other galaxies. Having said that, M86 looks anything but unique. The galaxy ESO 137-001, which we'll be looking at next, has a similar shape. But unlike M86, it appears more outlandishly original. Located 227 million light-years away from the Sun, it is as heavy as 5 to 14 billion solar masses. As for its stars, most of them are young and bright blue giants. ESO 137-001, in its turn, is part of Abell 3627, a large galaxy cluster. Moving to its center at an incredible speed of almost 2,000 km per second, the galaxy collides with interstellar gas pressure inside the cluster. As a result, its own gas is blown out, leaving behind tails that stretch for up to 260,000 light-years. Incidentally, the mass of interstellar gas in those areas is 2 to 4 times that of the gas inside the galaxy. It is hardly surprising that starbursts are a common thing here. That is, stars don't stop forming in these enormous streams made up mostly of hydrogen. When seen from the side, ESO 137-001 appears like a giant jellyfish floating through endless expanses of space. Unfortunately, as the galaxy is continuously stripped of its interstellar gas, its life expectancy diminishes too. With not much material left, no new stars can form here, which greatly affects the structure of the spiral arms and central bulge of the galaxy. On the bright side, scientists have a chance of finding out more about dark matter and its interaction with other space objects by observing the behavior of the gas streams left in the galaxy's wake. Speaking about the formation of new stars, there is a galaxy with a name that speaks for itself: Baby Boom. Around 4,000 stars are born here every year, which is about 400 times more than in the Milky Way. Straightforward calculations show that on average, a new star lights up in this area of space every 2 hours. The Baby Boom galaxy lies around 12.2 billion light-years away from the Earth. This means that what we see when observing it is what was happening just 1.5 billion years after the hypothetical Big Bang. It was a time when the universe was still in the process of forming its structure. What is taking place in the galaxy now is drastically different from what we expect to observe there in theory, based on what we know about star formation. The reasons why stars are produced here at such an astounding rate are not known yet, but it is beyond any doubt that Baby Boom is able to provide us with a lot of information about the early stages of our universe's evolution. One of the few galaxies one can observe through an amateur telescope is the so-called Sombrero Galaxy, official designation M104. It lies 30 million light-years away from the Sun, and its diameter is roughly 4 times smaller than that of the Milky Way. The Sombrero Galaxy's outstanding feature is a massive ring of dust and cold hydrogen enveloping it. Observations show that it is here that most young stars are born. In addition to the peculiar ring, the Sombrero Galaxy is also remarkable for its elaborate inner makeup. Observations with the Spitzer Space Telescope show that most stars in this galaxy form a structure typical of elliptical galaxies. The stars here are mostly rather old yellow and red dwarfs. The other stars here, on the other hand, form spiral structures concealed within an elliptical cloud. It is thought that this phenomenon is a result of 2 galaxies' collision, with their stars subsequently and almost inevitably mingling together. It is incredible that the galactic structures survived a merge of that scale with minimal damage, are none the worse for this tremendous collision, and can still be observed. Another peculiar feature in the Sombrero Galaxy is exceptionally powerful X-ray radiation emanating from the center. It is assumed that the accretion disk of a supermassive black hole may be its source. The mass of the hole is estimated to be over 1 billion solar masses, which makes this enormous object one of the most massive black holes known to science today. There are also several sources of tremendously high frequency or terahertz radiation detected within the galaxy, although today their nature is still a mystery. Our galactic parade today is concluded with yet another object boasting an elaborate inner structure, the eerie M64 galaxy, rather aptly dubbed the Black Eye Galaxy. The nickname comes from a dark band of cosmic dust that partly conceals the galaxy's center from the observer on the Earth. Due to this line of cosmic dust, as well as the exceptionally bright active nucleus, it is impossible to estimate the Black Eye's number of stars even roughly. What we do know is that it is comparatively small and not so remote. Its radius measures 25,000 light-years, and it lies approximately 17 million light-years away from the Milky Way. The Black Eye Galaxy is made up of two well-defined parts. Interestingly, the inner disk with a bulge rotates in the direction opposite to that of the outer ring. The most likely explanation for such a bizarre makeup is that the galaxy formed after two smaller ones collided and merged in the distant past. Admittedly, it would take a combination of a number of mutually independent factors for such a fascinating and well-defined structure to form. For example, the progenitor galaxies would have moved at specific velocities and come together at a certain angle. The odds of a success would have been minuscule. The Solar System is just one of the countless multitude of planetary systems scattered across our galaxy. As we know, it consists of a single star in its main sequence stage and 8 planets with their satellites. In addition, our system contains over 1 million small celestial bodies like asteroids, comets and meteoroids. The planet in the Solar System lying furthest, at least that we know of, is Neptune. Its orbit's radius measures around 30 astronomical units, which is equivalent to approximately 4 light-hours. Amazingly, only a tiny portion of the Solar System is encompassed by Neptune's orbit. The remotest object in the system discovered to date is the so-called Far Far Out, lying 132 astronomical units or 18 light-hours away from the Sun. Still, even this object, barely visible against a dark background of unfathomable space, is not at all close to the hypothetical Oort cloud, whose inner boundaries lie approximately 2,000 astronomical units away from the center of our system. According to some estimates, its outer boundaries stretch for up to 60,000 astronomical units at the very least, which is around 1 light-year. These limits are predefined by the Sun's gravitational influence, and what lies beyond is interstellar space. Moving further away, we will notice over 50 of all kinds of stars within 20 light-years from the Sun. These stars are really diverse, from dim and cold brown dwarfs to bright and widely known objects like Sirius, Procyon and Altair. Some of them have their own planetary systems, with objects potentially capable of nursing and sustaining life. For example, the object known as Gliese 832c, which is 16.1 light-years away from the Sun, is similar to our Earth more than any other planet within the Solar System that we know of. The average temperature on the exoplanet's surface reaches 253 Kelvin or 20 degrees Celsius below zero, and it takes the astronomical body just 36 Earth days to complete a full orbit around its parent star. In astronomical standards, the distance between us and Gliese 832c is relatively small. However, a space probe setting out from our system at a speed of roughly 17 km per second would take as much as 300,000 years to reach the exoplanet's environs. At our current level of technological advancement, it is impossible to design an interstellar spaceship capable of completing as long a journey as that. The Solar System, together with its neighbor stars, is part of the Orion arm. The latter, in its turn, is part of the Milky Way. It contains around 400 billion stars, and potentially over 1 trillion exoplanets of all sorts can be discovered there, according to estimates today. The main diameter of the Milky Way measures around 100,000 light-years, and the stellar halo may be twice as large. Even though the thickness of the main disk measures about 1,000 light-years, there is a clearly defined bulge in the galaxy's center. This bulge is roughly 3,000 light-years thick. The Milky Way is part of the so-called local group. This is a vast structure comprising over 50 galaxies concentrated within an area of space measuring around 10 million light-years in diameter. The Andromeda Galaxy, the Triangulum Galaxy and the Milky Way are the largest of the lot. Some estimates show that the mass total of the cluster may reach as much as 3 trillion solar masses, with our galaxy and Andromeda accounting for the major part. With the distance from the Earth to Andromeda around 2.5 million light-years, it is considered to be our closest galaxy, not counting smaller or dwarf ones. Moving on to the next order, the local group forms part of the giant Virgo supercluster made up of over 30,000 galaxies. The supercluster is located within an area of space with a diameter of around 150 million light-years. Its mass total is as much as 1 quadrillion solar masses, or in other words, around 1,000 galaxies like the Milky Way. The supercluster is quite flattened, and around 60% of all the objects it is made up of appear like a flat sheet around 10 million light-years thick. Staggering though it may appear on the face of it, this value is actually small in terms of the large-scale structure of the universe. As we zoom out still more, we have a chance of seeing a giant supercluster of galaxies approximately 520 million light-years in size. Called Laniakea, it includes several galaxy superclusters, among others the Virgo supercluster and the Great Attractor. The overall mass of this formation measures approximately as much as 100 quadrillion solar masses. The Great Attractor lies roughly 250 million light-years away from our planet and is the gravitational center for all objects lying close by astronomical standards. It cannot be observed from the Earth directly, as the Milky Way's plane thwarts it. That is why the nature of the Great Attractor still remains an unsolved mystery today. Laniakea is part of the large-scale structure of the universe, an elaborate system of galactic filaments, walls and voids, gargantuan areas of emptiness in space. Some of these objects are really incredibly enormous. For example, the Hercules Corona Borealis Great Wall stretches for around a staggering 10 billion light-years. Ever since its discovery in 2013, this superstructure has been considered the most gigantic component of the large-scale structure of the universe. To all appearances, it must be home to millions of galaxies, and the number of stars it contains will probably always defy calculation. The mere existence of a structure like that is a mystery to science, as according to today's accepted theory of universe's evolution, gargantuan clusters like that are simply not supposed to form. But incidentally, this wall, so enormous that the human brain cannot fully appreciate its dimensions, is still just a tiny portion of the observable universe. According to today's cosmological notions, space and the universe is continually expanding, with the speed of expansion depending on the distance between objects. The further an observed object lies away from the observer, the faster the distance between the two increases. The rate at which the two mutually recede is not limited by the speed of light, because it's actually space matter that is expanding, which means that at a certain point the two objects will be mutually unobservable. Relic radiation observation shows that the area of the observable universe is a sphere, with a diameter roughly 93 billion light-years. According to the theory of relativity, we can see and interact with only those objects that are within this sphere. This conventional spherical area in space is called the meta-galaxy, and it may be either all of the universe, or again its tiny portion. For all we know, Hypothetically, there may well lie some unknown structures beyond the visible boundaries of space. Such entities are referred to as extramegagalactic objects, and unfortunately it is impossible to study them today with scientific methods. Still, some astronomical bodies on the edge of the visible universe appear to be moving in ways different from what we would naturally expect, judging by the data we have. Instances of anomalous movements like those may be evidence of the presence of some massive structures beyond the metagalaxy boundaries. Their attraction pervades the space around and influences objects around too. There is a whole plethora of hypotheses as to the structure of the universe beyond the metagalaxy, but most of them are rather of metaphysical nature. For example, some people believe that time and space, as we more or less know them, are non-existent beyond the boundaries of the universe. The physical laws we're used to do not apply there either, and notions of matter, material, or energy are virtually senseless. This hypothesis is further elaborated on by the following idea. The metagalaxy accounts for just a part of a yet more complex and larger-scale superstructure in space whose makeup and dimensions are too incredible for us to imagine. It is quite possible that this structure could be in a multidimensional space, or else be based on physical principles we have no idea of. This makes the metagalaxy just an insignificant addition to or a partial reflection of this mind-boggling superstructure. According to some interpretations of the anthropic principle, there are other worlds out there beyond the boundaries of the observable universe. In those worlds, the values of the fundamental constants like the speed of light or the electron charge are completely different. This hypothesis is in many ways supported by the idea of a multiverse, which schematically appears as foam with lots of bubbles separated from each other by thin walls, but these walls are impenetrable. This makes every universe a separate space, with its own physical laws, and for all we know, these laws may be totally different from the ones we're used to. The most radical hypotheses go as far as to deny our world any objective reality whatsoever. According to these, the universe is just a simulation like virtual reality in computers, but on an incredibly advanced level. As a rule, ideas like that imply that there are some super beings or super civilizations out there beyond the reality we're used to, whose level of advancement is infinitely higher than ours and whose goals and capabilities are arcane and incomprehensible. However, it goes without saying that it is hardly possible to either confirm or repudiate these hypotheses. Of course, distances in space defy our imagination and are even frightening. They appear infinite from the point of view of any person today. What we do know is that the universe is expanding, and provided this process continues, there will come a point when space objects will disappear one after another beyond the event horizon. First galaxies, then stars, and the world will immerse in eternal darkness. But by then, there will be no one around to witness that. The famous American writer Ursula Le Guin expresses her own thoughts through a character in her book in these lines. The word must be heard in silence. There must be darkness to see the stars. The phrase has to do with the birth and death of all that exists. Every object in the universe has its beginning and its end. Some subatomic particles last as little as tenths of a second. Some microorganisms live between 2 hours and several days. Man's life expectancy counts several decades, but even stars eventually burn out after millions and billions of years of existence. And what about the universe itself? Is it also going to come to an end at some point? What will it be like? And what will happen after its death? The earliest theory of the genesis of our world is what is known as theory of the stationary universe or steady-state universe. Supporters of this theory claim that the universe has no beginning and no end, It has always been and always will be in its steady state of equilibrium. However, very soon scientific estimations proved this theory likely to be wrong, as there are some irreversible processes taking place in the universe. In the 1910s and 1920s, the Big Bang theory was formulated and widely popularized. Today, it is one of the most consistent scientific theories, and it is able to account for the universe's genesis and evolution. Dozens of scientists contributed to the development of the Big Bang theory, and Albert Einstein's works on the general theory of relativity laid the theory's foundation. The main conclusion this theory enabled scientists to arrive at is the supposition that the fate of the universe depends on dark energy, a theoretical type of energy causing space to expand. Be it as it may, at this point it is quite impossible to say anything definite about this physical phenomenon. There are a great number of theories about this, and each of them has its praiseworthy aspects and shortcomings. According to data we possess today, the age of the universe is calculated from the moment of the Big Bang, and is estimated at slightly less than 14 billion years. The universe is constantly expanding, and depending on the density of dark energy, it will either expand forever at a regularly increasing rate, or else the expansion will slow down and reverse. In this case, the universe is bound to compress into an infinitely small singularity, similar to what it originated from. Today, science is not ready to give a definite answer to the question which of these two possibilities will prevail. However, it is ready to suggest at least two equally possible scenarios of what may happen next, referred to as the Big Rip and the Big Crunch. The universe's expansion rate is proportional to distances between objects. The further some objects are located from each other, the higher the expansion rate. Imagine a balloon pumped with air. There are two dots on it. If we pump still more air into the balloon, the dots will get further away from each other. That's the way the expansion of the universe works. It is space itself that expands. The further the dots are initially located, the faster they get still further apart. At a certain point, this rate exceeds the speed of light. This point is known as the event horizon. All objects beyond it disappear from view, and they drift away beyond the reach of the most advanced telescopes, never to be observed again. Just imagine. First, the remotest galaxies and clusters will disappear from the sky. Then, one by one, the Milky Way stars will fade away, and to crown it all, it will be the turn for our Sun to go dim. What a gloomy sight. If the Big Rip theory holds good, the universe's expansion rate will be constantly on the increase. This will lead to expansion forces gradually overcoming gravity forces. Following that, first galaxy clusters and then galaxies themselves and star clusters will be broken up. After that, it will be the turn for stellar systems to disintegrate, as host stars will not have sufficient pull to keep their planets and satellites from floating away. At the next stage, matter will be reduced to atoms, and these will be reduced to subatomic particles. Matter will effectively cease to exist. After this, physical laws as we know them will cease to be, and any further developments are quite impossible to predict. Observations today show that space expands and the expansion rate is on the increase. However, we are not familiar with the nature of dark energy. It may well have properties unknown to us at this point, and these may reverse the expansion processes. As a result, the universe will start contracting. This may well happen if general gravitation created by all matter in the universe exceeds its expansion force. This scenario is what is known as the Big Crunch. In this case, processes in the universe will run in the same manner until its size decreases 5 times. Galaxy clusters will come together as one supercluster, which in essence will fill the entire universe, considerably shrunk by this point. Meanwhile, inside the galaxies, events like births and deaths of stars, planet formation and so on will keep taking place just like before. When the universe contracts 20 times more, its volume will account for just 1% of that of today's, and all galaxies will blend into one. The relic radiation temperature by that time will measure 274 degrees Kelvin, and it will still continue to grow. This means that there won't be any liquid water left in the universe, and water is vital for biological life as we know it. Further contraction of space will cause the universe to heat up even more. Planets will first be burnt and then melted. All matter will crumple into an enormous cloud of boiling plasma. After that, atoms and subatomic particles will disperse, and eventually the universe will collapse into a singularity similar to the one it used to be when it was born. There is a theory which is a kind of a spin-off of the Big Crunch theory. It is known as the Big Bounce theory. According to the Big Bounce theory, on reaching the state of singularity following the Big Crunch, the universe will be reborn as a result of yet another Big Bang, and the cycle will repeat itself again and again, supposedly forever, as far as it is possible to speak about eternity in conditions devoid of time and space. I will repeat myself yet again by saying that our knowledge about dark energy is too meager to speak about the duration of any of these scenarios. For all we know, the next Big Rip, or Big Crunch for that matter, will take place in a period when there are still stars and planets around. But what if it isn't the case? What will happen to the universe if its ultimate fate is still extremely remote in time? Still, the laws of physics imply that the universe as we more or less know it cannot exist forever. There are 4 clearly defined epochs in cosmology, and each of them is associated with this or that particular phenomenon. We live in the so-called stelliferous era. There is a lot of interstellar gas in the parts of the universe around us. It is used as raw material for stars to form from. New stars are born from this gas, and the process will continue until all interstellar gas has been depleted. This epoch is expected to be over in the period from 1 to 100 trillion years from now. By that time, the Sun and the overwhelming majority of other stars will have depleted their nuclear fuel, subsequently turning into white dwarfs, neutron stars or black holes. I've actually already spoken about it in an earlier video. The next era is known as the degenerate era. There will not be any main sequence stars around anymore. Most matter in the universe will remain in the form of white and brown dwarfs, and some matter will persist as neutron stars and black holes. It will take a great amount of time for all these objects to cool off, around a duodecillion or 10 to the power of 39 years. White dwarfs will gradually give off their heat in the form of radiation and become black dwarfs. As for brown dwarfs, they will cool off too. Thermonuclear reactions taking place in their interior at a sluggish rate will eventually stop completely. Gradually, most matter will be slurped by black holes. At this stage of the universe's evolution, dark matter annihilation and protons disintegration will be the major processes. The proton is a subatomic particle that atoms known to science are built of. It is considered one of the most durable subatomic particles. Its life expectancy, as it were, accounts for approximately 100 duodecillion, or 10 to the power of 41 years. Now, by the time this era comes to an end, matter in the universe will look like a great ocean of freely floating elementary particles with an occasional neutron star or black hole tucked away among them. The next era is the black hole era. According to some theories, black holes will form clusters and eventually blend together, thus forming one single gargantuan black hole. Alternative theories suggest that black holes will slowly evaporate while emitting energy before vanishing completely. Black hole evaporation is a quantum effect produced by what is known as Hawking radiation. The smaller a hole, the more intensive its evaporation, which eventually strips the hole of all its matter and energy. This process is supposed to persist for 10 to the power of 100 years. This number is also referred to as googol. Be it as it may, eventually only dead expanses of space will be left in the universe. This space will contain debris left over from processes having taken place in the previous epochs: photons, electrons, positrons, neutrinos, and quarks. Electrons and positrons will collide, thus causing annihilation. The universe may exist in this state practically forever, until the next big crunch or big rip at the very least. Either way, the humanity will be long gone at that time. Its existence is likely to be terminated in the stelliferous era. Our planet, meanwhile, will remain habitable for another billion years or so, and after that it will be burned by the ever-intensifying glow of the Sun. About 5 or 6 billion years later, our Sun, by then a red giant, will shed its outer layers and become a white dwarf. But what will happen after the universe dies? Disappointing as it is, there is absolutely no way we can answer this question. The trouble is, whatever the scenario, there won't be either time or space as we know them, even if the Big Bounce theory or the Big Crunch theory is right, or else a new Big Bang takes place, thus giving birth to a new universe with a fresh set of galaxies and stars. We will simply never find out. Just like we will never find out what it used to be like in the universe before ours, because the word must be heard in silence. There must be darkness to see the stars. Dear friends, this amazing journey through the universe has come to an end, but there are many more discoveries to come. Billions of stars and trillions of planets still hold their secrets, and it will take a lot of time and effort to unlock them. That means that there are a lot more new educational episodes about the mysteries of the universe up ahead. And let's keep in touch.